Hi. Hello? Yes, it works. Yes.
Okay, welcome back everybody. We're going to start today's session. The first speaker is Gigi Guzzo, who's going to tell us about challenges in current and future large-scale structure surveys in cosmology.
Okay, thank you, Martin. Good morning, everybody. I would like to thank the organizers to invite me to try and give this quick overview of some of the challenges that we are facing when thinking about using large-scale structure to learn about cosmology. So there are many things I won't talk about today. I will essentially concentrate on challenges related to redshift surveys, or large-scale structure as measured by redshift surveys. And in this plot, I just made a cartoon that some of you probably have seen already, in which we see the progress in sampling the universe around us from low redshifts. You have slow digital sky surveys. The luminous galaxies, both. These are all pretty wide-angle surveys, so covering large volumes, but peering into moderate depth, while surveys like Vipers that you see here have tried to push this same concept of surveys. In this case, is a complete survey of all colors and all galaxies with only a simple magnitude limit selection down to redshifts of the order of 1. This is so essentially the state of the art at these redshifts, and the future is essentially Euclid and Daisy. And I will try to, well, there are other things ongoing, of course, and apologize if I won't cover them. I will try to concentrate on challenges that come from the general task of analyzing this data and get unbiased cosmological information from these. And actually also trying to understand what do we really want to understand, what do we really want to learn from these surveys. Okay, what do we want at the very end is to measure information, to extract information for this very simple statistics, that is the power spectrum, or if you prefer, the correlation function. You want to get the signature of a number of effects that change the shape of this function. And so this is about the regime where for coming redshift survey we'll be able to sample. This is a plot from the Planck papers, and this is where cosmic microwave background observations dominate. And you expect to be able to do many things with redshifts and things that have been done already, but at a higher level of precision. You know, all effects that I'm not going to describe here, but that change your shape, and to the very minimal information, the overall shape of this function depends on things like omega matter, the baryon fraction. You know, there are wiggles from baryonic acoustic oscillations, and those are those that you can use as standard ruler to measure distance information, and so derive cosmology from them. So the final aim is that you want to get things like this. This is just one example of a forecast from the very recent, most updated Euclid forecasts. This is from the science performance verification document that is using all the machinery validated by this, what we call the IST, the Intra-Science Working Group Task Force on Forecasting. That there is a massive paper going through internal review at this moment, and this effort was led by Valeria Petorino, Ariel Sanchez, and Tom Kitching, and the hard contribution of many others is really a long-term work. But anyway, this is what you want to get from the shape of the function, essentially. But and also you want to use the anisotropy of that function. That is what actually the universe allows us to measure by distorting our maps of redshifts due to the fact that galaxies move. Galaxies move because of the inhomogeneous part of the universe. So from redshift surveys, you get both the background expansion information, and you can also get information about the inhomogeneous part, so the growth of structure. And we know that this is a very important probe of whether, well, some modification of gravity is a potential origin for what we see and we call dark energy. Although the two things are not really very distinguishable in many cases. So this is concerning the growth of structure. This is a kind of old forecast for Euclid, but still absolutely in the right ballpark compared to where we stand in this growth of structure measurements. I added the recent measurement from one of the measurement from EBOS down here, and this is what Euclid essentially aims to achieve. So the name of the game is 1% accuracy, or 1% precision, sorry, on the measurements. And this is what we have to face in terms of systematics. So these are the challenges. The challenges are to be able to use the abundance of data that we are going to build without, with the measuring things with the right tool, okay, not with a biased tool. And there are essentially two areas where you get systematic errors. One is observational effects, so how well you're able to handle your data, and the other one is modeling, essentially how able you are to connect your data to the theory predictions. And this is, there is a long way between one and the other, and I'll show you some highlights about this. I will add at the end a little comment about going beyond doing spectroscopy just to measure redshifts, and I will tell you what I mean at the end. Systematic effects are so important, and in the Euclid project, we even got a specific task force that looked into that and produced this massive document, which is unfortunately not yet complete, but is extremely rich, extremely interesting, led by Ariel Sanchez and Ben Granette, and with the contribution of a few other people. And here there is a very nice description of all the possible uncertainties. So let's start with observational effects. And given this is a general review, I'm not going to talk about Euclid in particular, but in general about what will happen. And so let me start with the DAISY. And observational effects, any way you try to get redshifts, when you build a multi-object spectrograph, your main aim is to get as many redshifts as possible in the shortest possible time. And so you build machines which try to cover your galaxy distribution on the sky in the most efficient way. Most efficient typically means filling the space homogeneously. This is not quite perfect if you have clustered distribution, and so this is going to affect your observed clustering. DAISY, for example, has a specific feature due to the fact that you position your fibers, okay, through a patrolling device which covers specific areas, and so imposes in the end the pattern on the sky. Well, you have to work this carefully, but people have shown that you can actually correct this very well. This is an example. This is work by Davide Bianchi and Will Percival, and what you see here is what you get if you have no weights. So these are the multiples of the correlation function, and that the mean and the corrected one goes exactly on top of the parent of the MOX. So you can actually do this. But this is something you have to think well in advance. In Vipers, we had the same problem. And actually, we recently applied the same technique to Vipers and got a little improvement in the accuracy of our correlation function measurements. This is, what you have to do if you want to achieve the beautiful predictions of this survey. This is one example of, again, from DAISY, a slide that I got from Will Percival. The precision expected in the measurement of the neutrino total mass and number of neutrino species. And this is about, a factor of more than 4 times better than Planck plus both BAOs. So again, you need to control your systematics if you want to achieve this. Going to Euclid, the situation gets complicated because, all the surveys, DAISY, for example, Vipers, in some way allows you to find a way to correct what you are missing because you know what you are missing. You know what is your parent sample. You have your complete magnitude limited sample, all galaxies on the sky down to a given magnitude, and you know what your selection function is going to select. Okay. Euclid is not quite the same. In Euclid, we use what is called the slitless technique, which is essentially you open your field, you put your disperser, and you get a spectrum for whatever you put in the field. Here you have a beautiful example of from an HST GRISM observation. So essentially, this is not what originally Euclid was supposed to do. I mean, when the spectroscopic concept was proposed to ESA, this included some devices called micromirrors, which are actually devices that are used in that machine, so in video projectors. And that was a way to build the slits in space without having to carve material or do things that in space you cannot do. But was still found too complicated for space, and so a simpler approach, slitless, was chosen, which actually makes it more complicated for the analysis of whoever. So no target is required, but Euclid will be really the first time that this is used on large scales. So this brings challenges, a lot of challenges. A lot of effort is devoted in the team about solving these challenges. This is a simulated Euclid field, and actually what you see very clearly are not galaxies, are stars, and the galaxies are just, the H-alpha line redshifting to the infrared is just marked by these green circles. So, and there are a number of effects that reduce the signal to noise of this data, and that you have to take into account. This is just a diagram on where the line visibilities will be in the redshift range of Euclid. Euclid observed between 0.9 and 2. So there is a lot of work being done to understand foregrounds and how these affect the redshift measurement efficiency. Well, okay, this is wrong. This is 2005. But the reason why slitless was chosen, because in some way, around this time, I mean, this paper in particular, is reviewed by Carl Glazebrook, stressed how space was beautiful because there was no background, and you could just do slitless, something that on the ground you better not do. However, life is different. Also in space, you have backgrounds, and you have the zodiacal light, which turned out to be quite a nuisance. And also something which also was realized during the development of Euclid is that you also get scattered light from bright stars that are outside of your field. So some of the light comes in, and this gives you a background that you have to that modulate the signal to noise depending where you are. Okay, so this is a full sky simulation which includes these effects. Okay, this is from the end-to-end galaxy clustering group that is doing this work. And so the role of simulations in this game is absolutely crucial, as well as in general everywhere in the analysis of data nowadays. But here in particular, we started doing simulations of the spectroscopic part of Euclid since the very, very, very beginning of the mission, because we wanted first to convince ourselves that this slitless technique could actually work. Okay, and so essentially, there is a full pipeline in this case. This is how you handle it. You take a cosmological simulation, you create mock samples that simulate part of your survey, or a good part, or as well as you can. This brings quite heavy computational problems, because producing a whole sky or a 15,000 square degree Euclid survey, or producing many of these, is actually not really easy. Okay. You add all the foregrounds, you superimpose your survey pattern, so all of the footprint of the survey on the sky, and you put it inside the simulator. And this will give you, fake measurements that you analyze, and you do cosmological inference, and you close the circle with the cosmology that you put in the first place. So to do this, there is a massive simulation together with many other smaller simulations. This is called the flagship simulation that was developed in Zurich, but under the supervision of these people. Joachim Stadel has been the main guy carrying this on. OK, moving on, after observational effect, let me spend a few words about modeling, which is the other side of the problem, because we like linear theory. We are able to do things very well in linear theory. The universe, however, is nonlinear, and most of the data are in the nonlinear regime. So you want to be able to use this data as much as you can down to smaller and smaller scales. Even if you have Euclid, even if you have DAISY, you go to such large scales, but you will have so much signal on small scales, and also so much information buried there that you actually can extract in some way. So this is an area where, of course, people in this room are spending a lot of time. So, and you have a number of ways to circumvent the big three, as Roman Scocimaro calls them. So, bias, redshift space distortion, and nonlinear evolution. This is what screens you, from your theory from the data, but also it's where a lot of information is included. These things do not come out by chance. They depend on the cosmology as well. So in some way, you can use them. And we use redshift space distortion, for example, to get cosmology. So you can go around this by improving your modeling, of course. There is an interesting point in adding higher order clustering. Okay, this is good for error bars. It is good for precision, but then leaves you the concern that maybe you are adding more nonlinear problems. And I'll show you something. On the other hand, they might, you might be affected by different systematics, and that would be good because there will be a cross-check. A very interesting point is, I think, is to try and optimize your tracers. We will have huge surveys. We will have many galaxies. And provided your survey has been built with sufficient information on your galaxy population, you might want to select subsamples, not just use all the data. Simply because some galaxies, like it nonlinear, some others are quieter and better describing your velocity field, for example. I'll show you some examples. On top of this, you can change your perspective and use actually forward modeling, which I think is very interesting. And Ben Granette is doing quite a bit of work with me on this, and it's probably an important, with improvement of our computing capabilities, I think this is going to be more and more important. Okay. And I try to give you a few hints about this. This is what you want to do in the end, just quoting a paper in which some of this redshift space distortion growth rate measurements are used to constrain GR. And so to do this, you can apologize for this slide. You're not supposed to read the formulas. It's only to show, refining your linear models means complicating your theory in the sense, you are trying to capture your nonlinear effects. And for example, in redshift space distortion, after this classic paper 2004 by Roman, many models are built around this structure, an extension of the so-called dispersion model that is going beyond the Kaiser linear model by adding extra term in which you include these functions, which are are basically power spectra, a cross power spectra between density and the divergence of the velocity field and the power spectrum of the velocity field. And these are things that you don't measure. You cannot measure. You have to model them. You have to get them from simulation. So one way, for example, something that we did some time ago in a paper with Julien Bell is to find better fitting functions for these quantities. And this allows you to hopefully improve a bit your model. This is the case. This is the Taruya TNS model, which is one of those most better performing. And then, of course, you test everything with mocks. These are Viper's tests, and this shows you the relative error you get on f sigma 8 as a function of the minimum scale that you include. You see, you are pushing to extremely small scales, and this is Taruya. It's a bit disappointing that the models are not really behaving so differently. Okay, even just the dispersion model, that you would say, well, it's missing some pieces. Still, well, yes, of course, Taruya here is going below 3%, and this is quite good. But here you have this jump, so you always feel a little bit uncomfortable. So yes, I will speed up because it's only 5 minutes. It's interesting what happens if you add 3-point information, so higher order information. This is something from work which is being done by Cristiano Porciani and this group. In particular, this is Victoria Jankelevich work, where you actually get a very, very significant improvement of the figure of merit when you add the bispectrum to the power spectrum to measure W0, WA. The question is, what about systematics? Because if you add the higher order clustering, you have a higher order. If you start from Gaussian conditions, you have higher order clustering because you have no linear evolution. So I think the systematic part of this still needs to be looked a bit into detail, more into detail. However, for example, if you use voids, which have become more and more fashionable and interesting, those include higher order information and might be a way to get different systematics and look at things in a different way. Okay, the other point is you could try to improve your tracers. So if you have a survey that gives you all this information about colors of galaxies and other properties, you can look you can try multi-tracers approach, which is a way, hopefully, to improve error bars. But most importantly, you can understand astrophysics and understand that galaxies behave differently depending on some of their properties. Like different galaxies trace differently the velocity field. And so this means that some subclasses of galaxies might be easier to model, might require less parameters, might give you smaller error bars, might give you smaller systematic errors. And this is, for example, the case when you use blue galaxies and red galaxies. And you see, this is the 2-point correlation function in Redshift space. What you see on small scales is essentially the nonlinear effect, so the high velocity dispersion component in galaxy clusters and groups. You see for the red galaxies, it's very conspicuous because they live in high density regions. The blue part is more dominated by the overall infall pattern. And so there is something that it might be easier to model, and this is indeed the case. So with Vipers, we used all these different things and put them there in here, which gives us different angles and hopefully different systematic errors. Let me speed up. Forward modeling very quickly. You try to model everything in a self-consistent way. You have galaxy counts of galaxies. So you have to give prescriptions for the bias, and to get this consistent with the density field underneath, and you cycle over different realizations of the density field, varying the power spectrum, varying the galaxy connection to the density, so the bias, and in the end you find the best posterior distribution for all your quantities, including galaxy quantities like the luminosity function, for example. Not in such an extensive way, just because of computational effects, is this kind of approach that is, using n-body simulations, but here, unfortunately, only 2 n-body simulations because you don't have the power to do more, to do actually comparison of different gravity models, rather than, again, going and measure your growth rate of structure from the data and then fit your models and try to get constraints. Here you go the other way around. You say, I take an embodied simulation. I assume, I try to do my best to create galaxies in the embodied simulation. And so attach my galaxies to the halos. At that point, I can compare my theory to the data everywhere, including the nonlinear regime, which is actually where modification of gravity are which is very sensitive to modification of gravity. Okay, so this is what Genoa did in this paper, which actually which shows that it's very hard when you modify GR very little. This is an f of r model with very small f parameter to see here. Immediately your multipoles in Redshift space are affected, and you cannot match the data. The most astonishing thing is that you fit, lambda CDM fits the data without any ad hoc assumption, which I found quite amusing. This is my final point, and I say, well, what I meant by going beyond spectroscopy, I suppose that by 2030, our wonderful data will show you just that the universe is general relativity with lambda, okay? And we don't understand what it is. We haven't found a dark matter candidate, so what should we do then? Well, I think we should go back to the basics and say, get more data, okay? And so study galaxy and structure formation in situ. So go above Redshift 4. We can do it. There will be 40 meters telescope, and so and because we need to find the cracks in the theory. There is something we don't understand. So probably this is just a message. It's something we looked at in this report in a group led by Richard Ellis, essentially studying the case for a large aperture spectroscopic telescope for ESO dedicated to spectroscopic surveys. I think I will leave you with this. I want to leave you with a positive note, though. They said that perhaps a varying equation of state for dark energy is just behind the corner. I just wanted to point out this recent paper using distant QSOs as standard candles, which, despite any attempt of the authors, which are very reliable people, to find the systematics, tends to show a deviation from a simple lambda model. It goes in a very strange region, I understand, but and probably there is something strange. But just to say, perhaps we will find something with Euclid and Daisy. So thank you very much indeed.
Okay, we have time for a couple of questions.
Diagram where you show the test with various of RSD models, including Tauria et al., down to very small scales. And to that small scale, I wonder what kind of bias model do you use? Are you confident about the bias?
Yeah. Well, we made both. We tried both a scale-dependent bias and the constant bias. I think in the end, again, if you use sensible tracers, you can do more simplifying assumptions. If you use red galaxies, certainly you have to use a scale-dependent bias. But that adds another parameter, and so the error bars become larger. So the De La Torre et al. Paper uses scale-dependent bias, while the Petot et al. I think used the fixed bias caused by Francis.
Yeah, a question about what you said in the beginning and the effort you made in terms of understanding systematics. So it was mainly focused on two-point correlation functions or power spectra. On the same time, you were saying that to exploit the full capabilities of Euclid-like observation, you need to go beyond power spectra. So how do you cross the two problems?
Yes, well, this is actually I mentioned very quickly at some point that it clearly adds a lot of information, and so the error bars become smaller. On the other hand, if you use higher order information, you are really using nonlinear clustering, and so once more, your accuracy of modeling and all these things become crucial. I don't think but I'm not sure. But I don't think the work of Cristiano already has such an exploration of the systematic effects. It shows that you get a lot, you gain in terms of figure of merit.
Yeah, in terms of statistical power,
yes,
but in terms of systematics, this is not explored, right?
No, that's my understanding of them. But I think yes, and we need to do that. Yeah.
Okay, let's thank the speaker again.
Okay.
Can you hear me? Does it work?
It's probably muted. Okay, it's okay. Good. This is the command.
Okay.
Shall I? Does the mic work? Can you? Okay. So thank you for inviting me, and I will try to talk a little bit more about the higher orders that were mentioned in Gigi's talk. I want to start with a few motivational slides. So basically, we have this wonderful standard model of cosmology. It has only 6 parameters. It fits very well all the data that we have available so far, and there are some nagging discrepancies. If you look at the sigma rate from high redshifts and low redshifts, they seem to systematically differ. And when you measure H naught, the Hubble constant from high redshifts and low redshifts, there is this famous offset. And the good thing is that, an important contribution to this standard model of cosmology and tight error bars is the large-scale structure analysis. This is something that Gigi covered in his talk. And one thing that I want to highlight is that all of the standard LSS analysis that we advertise, our flagship measurements that we put in our MCMC chains, comes from the analysis of 2-point functions on linear and semi-linear scales. So it's these BAOs, which are intrinsically large-scale features, and redshift space distortions on scales of 30 megaparsecs and above. And that's good. They are considered to be very robust and systematics-free. BAO is very robust. Redshift space distortions, there are some questions, but we believe we can make them work. And so in about 10 years, this picture will change. We will have lots of BAO measurements, lots of redshift space distortion measurements. I took this picture from the W1st report, where the big ellipse shows current figure of merit, and the small ellipses show projected figures of merit. So the basic idea is that these error bars will shrink. They will shrink, but unfortunately, there is cosmic variance. We have only finite volume, so the number of linear modes is finite, and we will very likely saturate that cosmic variance limit at lower redshifts where dark energy is important. And so if we discover something new convincingly, that would be great. But if we are still close to this lambda, and if we still have this nagging 3 sigma, 4 sigma discrepancies, that would be really annoying. And so if we are in that situation, we cannot do any more BAOs. We have to think of something else. So how do we further shrink these ellipses? I know there are many generic options. Currently, we're doing linear 2-point. So one option is to make this linear 2-point better, maybe do a better reconstruction, do some sort of smart weighting. This is good, this is safe, but again, this is limited. You cannot really break the cosmic variance barrier. So you can also give up. You can move to completely new probes, look at velocity fields, topological measures of large-scale structure, look at the voids. When I looked at the CosmoGold program, there are, I think there are talks covering all of this, so I'm really looking forward to learn more about these options. But if you want to stay kind of closer to the baseline, there are 2 things that you can do. One thing is that you can, give up on linear. You can move to smaller scales, probably with computer-assisted modeling. And you can also give up on the 2-point and move up in the hierarchy and do linear 3-point statistics. So in my talk, I will talk exclusively about this final option, linear 3-point, which Gigi mentioned isn't really linear, but the leading large scales. So just to remind you really fast what this is all about, 2-point gives you probability of pairs, 3-point gives you probability of triplets. This is in configuration space. In Fourier space, your power spectrum is a correlation between 2 modes, and your bispectrum is a correlation of 3 different modes. And this bispectrum is, in the end, a 5D function of cosmological parameters. You have 3 lengths, and you have 2 angles. You always have bispectrum. You start with Gaussian initial conditions. Perhaps there is a small amount of non-Gaussianity, but then there is nonlinear gravitational evolution. Then there is galaxy bias, which is also nonlinear. So there is always a bispectrum at lower redshifts. And from this picture, from this origin story, it's immediately obvious that you can use bispectrum to extract things like FNL, B1 and B2, the bias parameters, and even growth rate and omega m, because the nonlinear gravitational evolution depends on those. And those are wonderful things to do. In my talk, that's not really what I will concentrate on. What I want to do, my ambition is to measure this bispectrum, use it as a new standard ruler, look how it is being stretched by Alcock-Paczynski effects, how it's being made anisotropic by Redshift-based distortions, and measure distance scale, the angular distance and age, and measure the growth, kind of in a similar way that we do from the Bauer spectrum. So I'm not saying it's easy, but that's the ambition, 5-year plan. So the bispectrum, I mean, it's I think fair to say that it has been underused so far, and it's understandable because 2-point is easier, and it kind of gives you a lot. And a few reasons, not to be reluctant to do bispectrum is that it's difficult to compute, it's difficult to model. You don't gain as much. Gains seem to be incremental, and there is also this idea that you can get this information by reconstruction anyway. And so I would like to argue in my talk that most of these points are not really true anymore, or maybe were never true. We've made significant advancements. We have new algorithms, fast computers, so there is no difficulty to compute bispectrum. My postdoc can compute thousands of bispectra overnight on his desktop computer. I will also argue that it's not true that you don't gain. You gain only a little bit on top of the 2-point. And I will also argue that it's not the case that you can get this information with the reconstruction. The only point that I'm willing to concede is that it's really difficult to model. That is true. More difficult than the 2-point. My next slide is, it's my observation that is the most controversial slide. Usually when I present these things, people, that's when people start to make faces and shake heads, and they tell me that I'm wrong and I missed the factor of 2π. But I will make this point anyway, and if you disagree with me, please let me know. I would be happy to be proven wrong. But the statement that I will make is that it's not the case that the information content of the power spectrum of the reconstructed field is the same as the information content of the power spectrum of the original nonlinear field before reconstruction plus all the higher orders. So historically, my success when I talk to my senior colleagues like yourself in convincing them that this is the case is 1 in 5. I don't know, I may be preaching to the choir, so I don't know how you feel about this, but please let me know later. And when I say that it's not the case, I don't mean practicalities. It's not that you cannot do perfect reconstruction because there is shell crossing. I don't care about that. Even if you did a reconstruction perfectly and if you modeled higher orders perfectly, I don't think this is true. This is accidentally true for currently available data sets. For example, for BOST, this happens to be true. I think this is true for the CMB, although I'm not a CMB scientist, so I don't understand data analysis as well. And I think, and this is also true if you measure amplitude-like parameters, like A sub S, or not have sigma rate. Sorry, this should be a sigma rate. This should be a sigma rate, not have sigma rate. Okay, so let me move on. Just one more slide on this. So what reconstruction does is reconstruction makes your BO sharper. So for the unreconstructed field, you have your power spectrum with some BAO, and you have a bispectrum. Both of them you can stretch and use as a standard ruler if you can model them well as a functions of scale. What reconstruction does is it makes your, it removes the bispectrum and it makes your BAO peaks sharper. And this is good, but there is, I was unable to find any mathematical reason why for an arbitrary random field, this gain would be exactly equal to whatever you get by getting this extra 5-dimensional standard ruler. Okay, so enough about this. Now, before you do something, you would like to know, what you will get in the best case scenario if you are successful, hence cosmological forecasts. Just to remind you, very few basic facts about bispectrum and how it works. This shot noise scales as 1 over n squared, and the number of triangles, number of valid triangles, scales as k to power 6. And so you really get a lot out of bispectrum if you have a dense sample. When you increase number density, you gain more than you do in the power spectrum. And also, you gain more if you move to nonlinear scales. Like the difference between k max of 0.15 and k max of 0.2 for the bispectrum, I think, is a factor of 0.5 invariance. So it's, you will double your error, you will halve your error bars if you go from 0.15 to 0.20. And so the forecasts that I present, they were based on paper with Praful Gagrani. These are simple Fisher constraints. They are, not very realistic in terms of systematics and observational stuff. But we weren't trying to make precise predictions for specific surveys. We were trying to make more general points. And I think for that purpose, I think it serves well, sufficiently well. So what I'm showing here is this is expected error bar on sigma, expected error, inverse error bar on the growth rate that you would get from DESI if you measured your bispectrum and went up to k max of 0.2 and analyzed all modes and you had no systematics. And it's normalized with respect to the same thing that you would measure from the power spectrum. So this black line is what you get from the power spectrum. The squares and the circles are what you will get for the bispectrum. And I guess the main point here is that for the bright galaxy sample, which is a really, really dense sample, and that's where bispectrum does well, you get this factor of 3. So the claim here is that if you did the standard redshift space distortion analysis on BGS galaxies, and if you manage to model everything up to 0.2, your error bars on the growth rate would improve by a factor of 3. And then there is this main sample which has lower density, so it doesn't do as well. But it's still, you're doing slightly better than the power spectrum. And then this tail is simply the number density that drops, and shot noise makes bispectrum not so useful. Right. And so this is kind of a motivational figure. I don't really believe that BGS is low redshift, and I don't really, it would be hard to model all the bispectrum in redshift space up to 0.2, but it's nice to know that there is a factor of 3 in there somewhere, at least theoretically, even in the Fisher. So maybe we cannot get to that, but if you go halfway still, it's a big improvement. A factor of 3 is a factor of 9 in volume, or the square root of 3, a factor of 9 in volume. So that's pretty decent. You see the same thing when you look at the BAOs. So the idea here is that you take the bispectrum and you start stretching it and aligning BAO peaks. And again, doesn't work as well for the BAO, but still, where you have high number densities, you do well. This is again normalized to the power spectrum. You get factors of 1.5, and you see these things for all surveys, but they are most pronounced in surveys that look at dense samples like VGS. Double Ishurst is good. Probes like Atlas are good because they also have high number density. And so if these plots kind of look suspicious to you, it's probably because you've seen figures like this that show you signal to noise of the Gaussian and the power spectrum and the bispectrum. And it kind of looks from here that the bispectrum is incremental, and that's mainly because there is no such thing as signal to noise, really. When people say signal to noise, they usually mean signal to noise on individual bispectrum, power spectrum measurements in the beams. That's the signal to noise of the amplitude. And it is true that if you were measuring the amplitude, bispectrum would only be incremental, but there are different kinds of signals to noises. For redshift-based distortions, it seems to be working much better. Okay, so what I want to do now is I want to kind of talk a little bit about recent works in this direction, large-scale bispectrum three-point analysis. This is a very incomplete list of recent works. It's biased towards recent. It's biased towards large scales. It's also biased towards BOSS, because that's my bubble. That's what I know. And I wanted to mention two series of works. One was led by Zach Slavyan. This is where they used the three-point, the real space configuration space three-point to measure the BAO. And it worked reasonably well. There was a 4 sigma BAO detection and 1.7% measurement of the scale itself. When combined with the two-point function, I think it cut the error bars by 30%. And there were other series of papers led by Hector Gilmarin, where he used bispectrum monopole in conjunction with the power spectrum. This helped them because with the bispectrum, we are able to, amongst other things, break the degeneracy between growth and sigma rate. So we don't have F sigma rate, you have F and sigma rate separately. Now I want to talk a little bit more in detail about the work. It was a later work, not part of the BOSS analysis done by David Pearson, who is a postdoc at Kansas State. And so in this work, what we tried to do is it's very difficult to do the full bispectrum analysis, so we try to confine ourselves to bispectrum monopole and to only measure the BAO. So forget about redshift space distortion. So BOSS, you have 800,000 galaxies. This redshift range, a reasonable number density. If it was higher, it would be better. And we had about 2,000 Apache mocks to test various things and get our covariance matrices. So this is the bispectrum measurement. Bispectrum, in this case, is a 3D function, so there is no good way of plotting it. This is just a sequence of measurements in some arbitrary order. And this is a power spectrum for comparison from the BOSS. The BAO feature is clearer here and not so clear here. So the modeling that we did was pretty simplistic. One of the things that we tried to do was to see how much you can push the modeling and still get reasonable results. The scales are kind of linear. They go up to 0.16. We used the leading order PT expression for the bispectrum, but there were some nonlinear features. The fingers of God were added in. The damping of the BAO was added in. And then what we do is we measure two BAO parameters along the line of sight and across the line of sight. This is the covariance. Covariance was the most tricky part because we had 700 measurements overall. There are lots of bispectrum triangles. We had 2,000 mocks. I mean, this is doable. This is a well-defined problem, but you have to account for this, and you need to inflate your variance. We had to inflate our variance by a factor of 1.5. I think this was the leading, kind of term in the statistical error budget. And so this is what we got out. These are some BAO chains. You have two line of sight and perpendicular of the line of sight parameters. These dashed lines are what we call in our business alpha V's. It's a certain combination average of the two. And it wasn't, at least to me, it wasn't very obvious which way the principal component of this would lie, but it turns out lies in the same direction as the power spectrum. So you are basically constraining dA squared divided by h. And these are the constraints on that principal parameter. On these plots, on the left, you have the mocks. On the right, you have the data. Green is the bispectrum, and you can see how green is wider, obviously, than the red. But it's not, it's comparable. And so we were able to get a BAO constraint of 2.7 and a BAO detection of 4.1 sigma. I think I'm running out of time, so I will just jump to my, I will quickly show you this slide. I will probably jump through this slide. And I will move to the summary. And so my summary is that I'm kind of recently become excited about the three-point function. And I mean, my main motivation is that there seems to be more information than you would naively think, expect, at least for some samples that we will get in the future. And also, the standard PAO is kind of becoming boring. I mean, there is a lot of work to do, sub% level systematics, but 75% of my personal work is this boring stuff. But it's nice to do something exciting. And I guess the key point for me is that it seems to me that this problem is solvable in the end. So if perturbation theory doesn't work, if modeling doesn't work, if you have to resort to n-body simulations, I don't know, I personally feel like I would be more comfortable with n-body simulating large-scale 3-point statistics rather than small-scale physics. So that's all. Thank you very much.
We have time for a few questions.
So I hated that you put that slide of, usually people start shaking their heads because I started thinking about that and couldn't think. I mean, it's a very interesting question. No, I like that slide, sorry.
Okay.
I just wanted to ask you whether you can say more about that. Doesn't that depend really on what kind of information you're looking for? I mean, I can totally see, if you're interested in some cosmological parameters, probably, all the information is in the reconstructed. But, if you're interested in stuff that, I don't know, how gravity changes your non-linearities, in those regimes, then you need that information. I mean, you don't want to.
Right. Yeah. So
I guess it depends on what you are asking and what are.
Yes, and I guess that's so when people talk about signal to noise, generically they usually mean amplitude, and for amplitude it is true. However, the most important things that we do in LSS analysis are not amplitude. So BAO is the derivative of the amplitude with respect to the scale, and redshift space distortion is the ratio of two amplitudes in different directions. And for those things, it's not the case that the bispectrum information is incremental, unless I'm wrong. So I'm willing to concede that. But I guess what I'm trying to say is that I don't think there is a mathematical theorem that tells you that for a random field, for a Gaussian random field that evolves in time, it's always true that the field, information in the field is equal to the information in all the cumulants. That's always true. But I don't think it's true unless there is something really special about gravitational evolution, that the evolved field is information equivalent to the original field. And I think if the reconstruction works this well.
There is more physics just happening, right? I mean, you want physics to work and see what it does, right?
Right. So I mean, reconstruction works well because we have a sharp feature in the power spectrum, in the correlation function. If we didn't have a sharp feature, so I'm not sure that the gains would be as big.
Another question?
So naively, when you do the reconstruction, taking things to initial condition, we would expect the field to become more Gaussian, and thereby, what's the point of doing the 3-point statistics?
Right, and the point is that that Gaussian field isn't. So the motion of. So that Gaussian field doesn't have the same amount of information as the initial non-Gaussian field that you reconstructed. So that's kind of what I'm trying to contest.
So you're saying like the reconstructed field is still not fully Gaussian?
No, it is Gaussian, but that Gaussian field isn't equivalent to the evolved field in terms of information content. So I just contest this. When you move things, information doesn't conserve. Some information.
Okay, that sounds like a good discussion over coffee, right? Yeah. Let's thank the speaker again.
Oh, yeah.
Zoom?
Yes. It's on mute, so when you're ready, just unmute.
It's already working. Yes.
No, you need to turn it on.
No? Yes.
Okay, the final talk before coffee is Stefano Assome talking about what use are baryon acoustic oscillations.
Good morning, everybody. So it's a pleasure to be here to talk about my work. So today I will try to answer these questions. So what are the use of the baryon acoustic oscillation and why the linear point standard ruler? And this work is done in collaboration with Stefano Carsaniti, Ariel Sanchez, Ravi Shet, Glenn Starkman, and Edith Zahavi. Okay, so that's the outline. So one of the main goals that we want to achieve in cosmology is to constrain cosmological models from cosmological probes. And to do this, we usually combine different cosmological observations. In this way, we can break the genesis among parameters. So in this context, what we want from the baryon acoustic oscillations, we want what we call the purely geometric BAO. What are them? So using this purely geometric BAO, we can get accurate distance measurement that are cosmology independent. I will tell you what that means. So to do this, we found two ways. The first is the linear point standard ruler, and the second is the correlation function model fitting. So what are the BAO? Weakly. So initial fluctuation in gravitational potential, they are measured as temperature fluctuation in the CMB by the Planck satellite, very precise measurement. They shows up as baryon acoustic oscillation in the galaxy correlation function at late times, and they give us the acoustic feature. So what is interesting is that the baryon acoustic oscillation gives us what we call a standard ruler. This means that we have a preferred scale at early times, at late times, and this scale is the comoving length that has been traveled by an acoustic wave since the beginning of time, and we call this the sound horizon scale. And this corresponds roughly to the position, to the peak position in the galaxy correlation function that we measure at late times. And what is interesting is that RD, the sound horizon, is a geometrical quantity, so it's independent of the primordial fluctuation parameters. So we can build in this way the ruler. And so then I want to stress, but you know this better than me, why BAO are important for cosmology. These are one of the most constraining late time observable. So for instance, here I show two examples. I will not discuss about them, but quickly. So here they combine CMB, BAO, supernova, and cosmic chronometers to do a dark energy, to do a study of the equation state for dark energy in a model-independent way, using a model-independent reconstruction technique. So here, what they do is they found a way to use BAO to do model selection. So they create fake KWCDM data. They analyze them as WCDM with the wrong model. So here, they show that if you consider APDV, that are just combination of the Hubble parameter and the angular diameter distance, you can use the BAO alone to do model selection, as you see this strong tension in the parameter space. Okay, so if this is the goal, what do we want from the baryon acoustic oscillation? So we want to measure cosmological distances that are estimated under the following theoretical condition. We want a measurement that is geometrical, so it's independent of the primordial fluctuation parameters. We want a measure that is independent on the dark energy model, so we don't want to assume lambda CDM or quintessence. And we want a measurement that is independent on the spatial curvature. And also is independent on the tracer that we are targeting with our surveys. And we call this the purely geometric BAO. So in practice, what we do, so in practice, we want to work in comoving coordinate, but since we measure angles and redshift, we have to assume a fiducial cosmology and work in comoving fiducial coordinate. And because of this, we are affected by the Eichelpaczynski effect. That this means that a sphere in the right cosmology will look like an ellipsoid in the wrong cosmology. Okay, so this distortion can be computed precisely for the two-point correlation function monopole in Redshift space, and this is the data. This is the distorted correlation function. It's related to the true correlation function by this alpha parameter, where alpha is called the isotropic shift, and this is defined in terms of dV. That is just a definition, and is a function of angular diameter distance and age. Okay, so we want to measure alpha, to measure distances, to measure dV in a model-independent way. And so we have to be careful when we use this equation. On the left-hand side, the Alco-Paczynski equation. On the left-hand side, we have data. On the right-hand side, we have theory. And we should be careful not to introduce unwanted dependencies in this game. So what complicates the games is are the correlation function nonlinearities in the BO regime. So we have effects such as linear gravity, Redshift space distortion, scale-dependent bias that distort the BO feature in the BO range of scales. So these are relevant effects that should be taken into account. And so here I show what I call the minimal model for the correlation function. It is the basic model that takes into account the dominant effect of nonlinearities, and this is used for BO analysis. And so it's simple. We can quickly analyze the cosmology dependence of the template. So P linear, the only relevance dependence is the energy densities and NS. A depend on lambda CDM. A is scale dependent but time dependent for these models. Lambda CDM, smooth quintessence, clustering quintessence, and we don't have to assume flatness. So for flat and unflatted geometries. Sigma naught, the damping parameter, depend on the growth, on the dark energy model, on the curvature, and on the tracer. Okay, so we should keep this in mind and go to the next slide. So here I show what is the BA only fit, that is the official standard BAO, that gives us the official standard BAO result. So here basically the minimal model is employed, and another broadband term, this polynomial, is added. And so we are fixing the cosmological parameters and the damping parameters. And this broadband term with these parameters is varied over also B. This B, basically the bias, the amplitude. And what we are after is alpha, that gives us the cosmological information. So the assumption here is that this broadband term takes into account a model nonlinear effect, and also the fact that we are fixing the cosmological parameters. And for this reason, because of the cosmological parameter fixing, we need to rescale alpha with this prescription, where RD is the sound horizon, F is fiducial at the fiducial value, and RD is the true sound horizon. So because of this prescription, we can ask if the error bars on alpha are properly estimated. And after a lot of thinking, we understood how we can do this fit without fixing the cosmological parameters. So that's the Alco-Paczynski equation. And now we have that all the relevant parameters are weighted over. And this way we can properly estimate dV. But that's it's a problem because, I mean, we measure dV with an error that is roughly 100%, or the 100%. But then we realized that if we, from these parameters, we compute a secondary parameter RD, then RD and dV, they have similar error, and they are very highly correlated. So the ratio of RD over dV is very well constrained. So now we can compare the error propagation, the errors, for the correlation function model fitting and the BA only. And what we get is that I use a Fisher matrix approach as a first step. And what we got is that the error bars of the BA only are underestimated by nearly a factor of 2. So it's good that we understand how to do this properly. But still, there is a question: how do we really know the galaxy two-point correlation function model? I will come back to this question later. But before, I want to show you a complementary approach. So this approach probably dates back to Peebles in the 70s. And the idea is that the observed correlation function is related to the matter correlation function of Redshift 0 through this factor that is scale independent for lambda CDM, smooth quintessence, clustering quintessence, and we don't have to assume flatness. So the point is that if we measure a per Fair scale in the correlation function, this will be time and model independent. So we can measure dV in a model independent way. Okay, so the idea is old, and people wanted to apply this, actually they applied this to the peak position 10, 15 years ago. But then it was discovered that the peak is quotient shifted by a linear effect as a linear gravity, redshift space distortion, and scale-dependent bias. So we cannot naively use this as a standard ruler, as a simple standard ruler. So for this reason, we have been looking in the bio range of scales, and we found a new standard ruler that we call the linear point. And what that is, so if you take a closer look to the correlation function, there is the usual peak, but also there is a dip at smaller scales, and there is the linear point that is nothing but the midpoint between the peak and the dip. So it has interesting feature. It is a geometrical point. It's redshift independent at 0.5% level, so it's linear. And this is because it's weakly sensitive to nonlinear gravity, redshift space distortion, scale-dependent bias. So exploiting these features, we can perform model independent distance measurement. So how that works? Okay, so from the nonlinear correlation function for the observed correlation function from the MOX, we can measure this quantity and apply a simple redshift independent correction of 0.5%. And this way, you are able to be accurate at 0.5% level. And what is interesting is that exploiting this feature, we can do from the data, when we apply this to the data, we can be independent on the correlation function model or template. So how does it work? On the left-hand side, we have data. And here we use a model-independent parametric fit to extract this quantity, this one. And on the right-hand side, we can use linear physics, like a Boltzmann code that we know much better than the nonlinearities. So that's how the game works. And we apply this to the Bose galaxy samples, the low Z and C mass ones. And we estimate the linear point from the two samples. And we compare this with the only Bose distances. And what we found on the pre-reconstruction data, what we found is that we have a consistent result with slightly smaller error bars. That's interesting and maybe convenient. So then we did a theoretical investigation where we wanted to check, compare the linear point errors to the correlation function model fitting, where all the parameters are varied over. And so what we found is the linear point is always more constraining than the correlation function model fitting. And so here we have two different rulers, as you see. So it's also important to stress that from CMB, for instance, or we can do also theoretical analysis with CAM, we get the same percentual error for the two rulers. But again, there's this question: do we know the correlation function theoretical model? What do we know about it? So to answer this, I will try to answer the question of the title: why the linear point? So when we use a correlation function template, we should keep in mind that we don't really know, or if you want, there is no agreement in literature, on how to model nonlinear gravity, space distortion, halo bias, galaxies in halos, which model to use, and what is the range of scales when this theory works. So the standard way to deal with the data is to validate the correlation function models as estimators, like to, for instance, to decide on which range of scales to fit. And so the main rule that is followed is to avoid parameter bias. What about the error estimation? So the linear point is complementary, and then different feature is a new observable. And because of this feature, we can do a model-independent. We can use a model-independent estimator. We get, maybe by chance, smaller statistical errors. We are affected by embodied systematics and by the 0.5 intrinsic bias. So a common problem for everyone is that we do have ab initio simulation for dark matter that are nearly convergent. But what about galaxies? We don't have ab initio simulations for galaxies. So to conclude, so it's important to have properly estimated error bars for VAO. And we want to measure cosmological distances in a way that is independent of cosmological background model, We identified two ways to do this. The first one we call correlation function model fitting, when we found a way to propagate all the errors. And we found that the errors of the standard VAO, they may be underestimated by nearly a factor of 2. So then there are still questions. Which model should we use? How many parameters should we employ? Can be then reduced somehow? On which range of scales should we fit? And then we propose another approach. This we call the linear point standard ruler. And is model independent, meaning that we don't need to know the correlation function model, and give us up to 50% more precise error bars with respect to the correlation function model fitting. So then we should keep in mind, to answer the first question of the title, that VAO distances are not good for all the possible cosmological models, in particular for non-standard cosmologies. They may have not been tested. So for instance, if you have modified gravity, this can give up a preferred scale in the game that can somehow spoil the standard VAO feature at some level. Some best fit and errors, they may be wrong. So there is a lot to do. We want to break the genesis among dA and H. And to do this, we want to include the quadrupole information. So then what happens if you have massive neutrinos? Can we use the VAO or the linear point to constrain neutrino mass? And can also measure deviations from a lambda CDM growth rate from the VAO. Can we work in Nankovian redshift instead of working in moving coordinate? What are the light cone effect? Are the linear point properties stable? So then what happens if you have different galaxy populations, clusters, quasars, 1 centimeter, and so on? Thank you.
Okay, we have time for some questions.
So I get that the linear point you define somehow, is not biased and get better results. But I was wondering if there is a physical meaning also behind this value, because you just average between the maximum and the minimum and put it as some kind of a
for now, we don't know. Maybe. We tried a little bit. But what we have, that is the feature that we can use and is stable, so that for cosmology. So it will be nice to understand better why, if there's a mathematical coincidence in lambda CDM and similar models, or if there is something deeper. That's an interesting question.
So when you showed your plot for the loci from the BOSS sample, BOSS data, how did you really determine which is the dip and the peak here? Because it's noisy, right? So
yeah. I couldn't give you all the details. Here, what we use is a model-independent parametric fit. So we use the simplest that we could think about, that is a polynomial, and we validate this with the BOSS mocks. But then you can use Gaussian processes, whatever is model-independent. Maybe we can get better results. So that's, yeah.
Okay, if there's no further questions, let's thank all the speakers again. We should come back at 11 o'clock.
I was explaining. I mean, I'm expecting some aggressive. You didn't tell. You didn't understand. No.
This thing we discussed, right? There's physical meaning of the linear point.
Yeah. No, that's but maybe it's a mathematical coincidence. That's really so far what we.
The microphone back.
Ah, sorry. It's not the first time this happened to me.
Everything you say will be broadcast.
Forever.
Have you thought of trying this in the laminar for forest?
Yeah, but that's, I mean, I am not expert enough.
But in terms of the modeling, right, it's interesting because there's another nonlinear.
It's another model,
right?
So far it's for clusters. It's not clear anymore for maybe.
I'd be curious. thanks for sending those ancient data.
Yeah, it was really hard to dig those.
Yeah.
Oh, I made a nice paper.
Yeah, did you see the paper?
Oh, yeah, I did.
Yeah.
It's great.
So I think it's going to be an interesting case. We're just we're just starting to develop it now, but the plan is to.
I mean, you mentioned it briefly in your talk, right?
Yeah. No, I think it's going to be really cool.
It's a fantastic idea. When I heard your talk, I thought like, oh, maybe that's something I want to do.
Yeah.
So,
Yeah.
so that's many LSSD, right?
I didn't talk about Euclid, right? But Euclid, you can do BZK selection really nicely. We mentioned it briefly in the paper, but I think there's a ton to be done. We just kind of scratched the surface.
Yeah.
Just revisiting all of these old galaxy formation cases for cosmology.
Oh yes. Yeah. I'd love to do that again. It was fun back in the day, and then I kind of didn't do it anymore. So there's no
more the merrier.
Science case to do that. Yeah. Sounds like it.
Okay, everybody, welcome back. We'll start this session with Hendrik telling us why weak lensing surveys are still evolving.
Thank you. Can you hear me? I guess that's a yes. So hi, everybody. First of all, I'd like to thank the organizers for the invitation. It's a great pleasure to talk about the current state of weak lensing surveys, and in particular the challenges we are facing here. So we already heard about weak lensing from Tim and Anya yesterday. They were talking about cluster lensing, where you have like one dominant mass in your field of view, and you also know where the mass is. So what we're doing with cosmic shear experiments is slightly different. We try to take all the information that is there in our images to really infer where the mass is, how it's distributed. And I always like to compare it to this picture here, which obviously shows you a pool seen from above. And if you now make the assumption that whoever laid the tiles on the floor of the pool did a good job, put them at right angles, then from the observed pattern that you see, you can infer the surface of the water. And from that, you might be able to infer parameters of the pool, like the water depth or the wind speed that creates these waves. And this is actually very similar to what we're trying to do in cosmic shear. So this is illustrated here. Unfortunately, we don't have this regular grid. So we have to take background galaxies. So if you have a lot of background galaxies, instead of making the assumption that you have a regular grid, you make the assumption that the ellipticities of these background galaxies are randomly oriented. Now, the light bundles, the elliptical light bundles that are sent out by these galaxies travel through the large-scale structure and get continuously deflected. Fortunately, you cannot measure the deflection, but these deflections also go hand in hand with the distortion, and that you can measure. Because once the galaxies land on your detector, they have a tendency to point in the same direction. And that's exactly the signal we are looking for. So in cosmic shear, we're trying to measure how strongly galaxies are pointing in the same direction as a function of their separation on the sky. So that's a two-point function. That's interesting because it's directly related to the statistical properties of the matter distribution that's actually causing this lensing effect. And it's also related to geometry because these light bundles travel for a long time, and so the universe is expanding, so you're also sensitive to that. From an observational point of view, the two things you really have to measure is the galaxy ellipticity, so you need high resolution images to measure axis ratios of galaxies and their orientations, and you have to get a redshift estimate. And since we're talking here about tens of millions of galaxies, or in the future even billions of galaxies, we have to use photometric redshifts. So we take images in different color bands and then infer approximate redshifts. Now this is imaging data that we typically use from the kilodegree survey that I'm involved in. The galaxies you are seeing right now on this projection are not the galaxies we are really using. There's lots of little specks here in the background. It's very hard to see in this projection, but those are the galaxies we are after. Those basically give us this grid to stay in the same picture that delivers the information for us. And this is not an easy process. So if you have a galaxy that's getting sheared by maybe 1% or so the axis ratio changes by 1%, it's a typical shear we're working with, then the light goes through the atmosphere, gets blurred out by the seeing, then it goes through your telescope, gets further distorted, lands on your detector where you only measure flux in certain pixels and you have noise on top. Now you have to infer the shape of this galaxy from that noisy set of pixels. Now, the way to do this is to use stars. So you first have to identify stars on your image and then measure the two-dimensional light profile of these stars, the point spread function, because the stars experience all these effects, the seeing, the camera, and so, but the light from the stars isn't sheared, and you know that they are point sources. So from that information, you can then deconvolve basically that image to get an estimate of the shear. So in practice, there are two different kinds of methods to do that. You can either work with brightness moments of the galaxies, or you can do model fitting. You assume that galaxies follow a search profile or so, and then you fit that to your data. I can't go into the details of these methods, but basically all these methods come with biases. You have noise bias because of this very noisy nature. The object that I showed you before was a very nice example. Most galaxies we're using are actually much more noisy. And you might also have model bias because the model you assume, like the search profile I mentioned, might not be correct. So the way to calibrate this is you set up large image simulations that are as realistic as possible, and then you run your shape measurement code on these image simulations and see whether you get the answer that you put in the beginning. There's another way to do this, and that's actually you take your imaging data and you shear the pixels. And then you run your shape measurement method. And since you know what kind of shear you put in, you can compare this to the original one. And so you can get a feeling for what's the response of my shape measurement technique to a known shear. That's called meta-calibration. In the end, you typically check for residual biases by doing two different kinds of null tests. So you can cross-correlate the ellipticities of the stars, so basically the Psf, to the corrected ellipticities of your galaxies, and you better find a zero signal, because otherwise, if the galaxy still knows something about the Psf, your Psf correction wasn't correct. And you can also do a B-mode test, so you basically look for curl patterns in the ellipticity distribution, which are not created by gravitational lensing. So this is also a warning sign. If you find these B-modes in your ellipticity distribution, then something might have gone wrong. All right, the second ingredient that I mentioned are photometric redshifts. So typically you have a sample of galaxies, maybe a few 10,000 or so, where you know the redshifts. And you can compare your photometric redshifts to the spectroscopic redshifts, and that's shown here. So you get a pretty good correlation, but there are systematic structures, there are catastrophic outliers, and you need to know where those are. So what you do then is you cut your sample into tomographic bins. So these are horizontal cuts in this plot. And then you do a measurement of this weak lensing cosmic shear effect with galaxies from each of these bins. And then you get a plot like this. So this is what we call a two-point shear correlation function, here multiplied by the angle theta. So it's just a quantity that tells you how strongly galaxies are pointing in the same direction as a function of their separation on the sky. So you take all galaxy pairs with a separation of, say, 10 arc minutes and check whether their ellipticities are correlated in some way. And you can also take pairs where one galaxy comes from one bin and the other galaxy comes from the other bin. That's all these off-diagonal cells here. And each cell contains different information because you probe the matter field in a different way. Now, the very attractive thing about this two-point shear correlation function is that it's very directly related to the matter power spectrum. So this is the quantity we're measuring. This is the averaging over these ellipticities. And that's how it's related to the power spectrum. So here's the total matter power spectrum. You do a line of sight integral and then a Hankel transform, and you arrive at the two-point shear correlation function. And really, the theoretical appeal of gravitational lensing is that there's no astrophysics involved here. This is basically just GR. Once you have a matter distribution, you arrive at the two-point shear correlation functions without knowing anything about galaxy evolution. So that's what makes it different from, say, galaxy clustering or so, where you always have the galaxy bias in there. Now, there's one complication. You have the distance distribution down here, and that's related to what I just mentioned. You have to estimate the redshifts of all your galaxies in the different tomographic bins. For a given cosmological model, this translates then into a distance distribution. So we basically need a calibration sample, like the one shown here, to estimate the redshift distribution of the galaxies in these bins. You cannot do this directly, so you cannot take just the spectroscopic redshifts of the galaxies that you see plotted here. because spectroscopic surveys, like the ones plotted here, typically use a different selection of objects than the weak lensing catalogs that we are using to measure this effect. So in a picture, it looks like this. This is G minus R versus R minus I color space. And if you look at the distribution of a lensing sample that's shown here in red, and a spectroscopic sample might look like what's shown here in blue. So what we then do is we apply a reweighting technique. So we basically take the ratios of the densities and assign those to the spectroscopic objects at each position in this plane. And then you get a much better match. So you make your spectroscopic surveys representative of your lensing sample. Now, we don't do this in two-dimensional space, as shown here, but in as many dimensions as we can. The more dimensions, the better. So that's why you want to have many images, many bands that you observe your galaxies with to improve this redshift calibration. It's clear that this can only work if you span the whole volume or hypervolume in this high-dimensional space with your spectroscopic catalog. If there are parts missing, then you get a bias. And it's also important that the color redshift relation is unique, and that, again, works better the more bands you have. If you have few bands, then you might get degeneracy, so galaxies at different redshifts having the same colors. So once you do that, you get an estimate for your redshift distributions. You just then take really the weighted histogram of your spectroscopic redshifts, and as shown here, again, for the kilo-degree survey. You still see some large-scale structure there, especially at low redshift, because volumes of these pencil beam spectroscopic surveys are small. So yeah, you can estimate errors on these distributions by doing a resampling of your spectroscopic sample. That's the regions that you see around these average lines here. Nowadays, we can get the mean redshifts of such redshift distributions that we use for lensing down to an uncertainty of 0.01 to 0.02. So that's the current state of the art, and it's roughly what we need for stage 3 cosmic shear surveys. For stage 4 surveys like Euclid and LSST, we have to do an order of magnitude better, and I think this is really one of the hardest things we have to solve until then. You also need to estimate a covariance matrix. In the past, that was usually done from n-body simulations where you have large mock catalogs and different realizations. Nowadays, most people prefer to do this analytically via a halo model approach, taking into account your survey footprint and so on. There are some nuisances that unfortunately destroy this nice picture that I just painted. And one of them is intrinsic alignments. So this very basic assumption that I mentioned, that galaxies are randomly oriented on the sky, is not totally true. So you might imagine having two galaxies forming in the same dark matter halo. They might have a preferential alignment with respect to the center of the halo. That's what we call the II term. So these are correlations in the ellipticities that are not caused by lensing, but are caused by tidal effects. And you also have another effect that mixes lensing and tidal effects. It's called the GI term, where a faraway galaxy is lensed by a dark matter halo that is intrinsically aligning a close-by galaxy. So you have to take those into account when you model your signal that I just showed you. We know the effects are small. We know this from spectroscopic surveys where we actually have an estimate of the local density, but we still don't know the exact amplitude of these effects. So we have to marginalize over possible reasonable scenarios here. The same is true for baryon feedback. So you have the total matter power spectrum in this equation that I showed you before. The total matter power spectrum certainly is modified by baryons. It's not just a pure dark matter power spectrum. And this effect yeah, is at the 10 to 20% level at these kind of scales here. You see here 4 different simulations, more recent simulations, that give you a rough idea of how large our uncertainty is on this correction. So again, you have to marginalize over all reasonable alternatives here to not bias your measurement. Now this only happens on very small scales, so it's not a large effect that affects all your scales. Oh, by the way, there will be something about this in the next talk as well by Marika Asghari. Okay, so much introduction. Now let's talk about the experiments that are actually going on right now, which we call the stage 3 surveys. There are 3 experiments that are trying to measure cosmic shear tomography at the moment. The American-led Dark Energy Survey, the Japanese-led Hypersupreme Cam, and the European Kilo Degree Survey that I'm involved in. So they try to measure the same thing, but they approach it from slightly different angles. So the technical realization is slightly different, which is good because that gives you some redundancy and some complementarity. So here in this table, I just tried to highlight where each of these surveys excels. So the dark energy survey, they have the largest camera, so they also in the end going to cover the largest area on the sky. Hyper-SupremeCam is done with the 8-meter Subaru telescope, so they can go really deep, and that also increases the number density of objects. Again, to be in that picture, to increase the density of the grid that you can use. Kilodegree survey, so that's us. We use a pretty modest-sized telescope, but it's the first telescope that was actually designed for weak lensing. So from the very beginning, people kept the optical distortions to a minimum. For example, put the camera in the Cassegrain focus, which makes the Psf much more well-behaved than for a prime focus camera. But maybe the biggest advantage of KITS is that it has a sister survey, Viking, that adds these 5 infrared bands here. So KITS and Viking is the only survey combination at the moment that does what Euclid is going to do in the end, combine optical data with infrared data. In that sense, the redshift calibration that I mentioned should be more robust for Euclid, and also the shape measurements because of this effect here. So in a nutshell, DES and HSC will have smaller statistical errors once they're finished, but our hope is that KITS plus Viking will have the better control of systematics. Okay, let's jump to the results. This is a plot from the Dark Energy Survey Year 1 analysis showing omega matter versus sigma 8. DES contours are shown in gray. The KITS optical only, so without the infrared still, contours are shown in blue, and the Planck 2015 constraints are shown in green. Here they marginalize over neutrino mass, so that's why the Planck contours are extended. And you see the picture that we already saw yesterday in several talks, that in general the lensing constraints give you a somewhat smaller S8. So this S8 parameter, which is basically the parameter that lensing measures best. With DES, you wouldn't really speak of a tension. There's still some overlap between Planck and DES. With KITS is a bit further away from Planck, so you might call this a mild tension. So it's interesting to see what's going on there. Shortly after that, the Hyper-SupremeCam team also published their first cosmic shear analysis. Their S8 that they're getting, shown here in red, is very similar to what DES finds, but their omega matter is much lower, which looks a bit curious. But in general, these lensing surveys agree with each other. There is a caveat, though, because some of the systematics modeling in these surveys is the same. So they use the same kind of nuisance parameters for the intrinsic alignments or for the shape measurements. And those nuisance parameters aren't constrained by the data. So the larger you make the price, the better the agreement between these surveys looks like. So that's something to keep in mind here. And they're affected by these effects in a similar way. So it's not a purely statistical error contour that you see here. Half a year ago, we published the first combined analysis of KITS and Viking. So the constraints are here shown in blue. Underneath, you see in green the KITS optical only contours, or you rather don't see them because the constraints are very similar that you get from optical only and optical plus infrared. I'm always saying I spent 2 years on getting the same result again. But one thing that is not shown here in this plot is certainly the systematic robustness. And we think that the optical plus infrared constraints are systematically much more robust because you can do the redshift calibration more reliably with the 9-band photometry that we have. Also shown here are now the Planck legacy constraints that came out in the meantime. So there you have a roughly 2.5 sigma difference, tension, whatever you want to call it, between the KITS constraints and the Planck constraints. Now, can we understand why DES and HSC give us slightly higher S8 than KITS? And I think we can. So this is a paper from this is a plot from our KITS paper showing many different tests that we did. So this shows S8 here. This is the fiducial result. And I want to highlight a few data points here. First of all, these 5 data points here in the middle. So that's basically taking different assumptions on the astrophysical systematics that we have, the intrinsic alignments and the baryon feedback. Varying assumptions in the reasonable range gives you that kind of scatter in the data points. So this is relatively unimportant. Like baryon feedback only really modifies the smaller scales, and intrinsic alignments are so small that they also don't do very much to your data. So compare this now to this set of data points where we take different approaches on how to calibrate the redshifts. There you get much more scatter, like on the level of 1 sigma or so. The results shift around depending on what kind of redshift distribution you're using. So I think this is currently the most serious systematic effect that we're facing, how to calibrate the redshifts. It's like a century-old problem in astronomy. How do you add the third dimension to your two-dimensional images? And here again, we're exactly facing that problem also with these cosmic shear surveys. I want to highlight one particular data point, and it's this one. There, we've taken actually not a spectroscopic catalog to calibrate our redshifts, but we took the Cosmos 2015 PhotoZ catalog. So that's a high-quality PhotoZ catalog that's based on 30-band photometry, basically one of the best PhotoZ catalogs that has been published so far. And we use that as a reference to calibrate our redshifts in kids. And then we see that our S8 goes up by 0.6 sigma or so. Now compare this to the two data points from DES and HSC, and you see we're very close to these data points now. Interestingly, these two surveys also calibrate their redshifts with this high-quality PhotoZ catalog from Cosmos 2015. So that's intriguing. Why might this happen? Well, it's a very good PhotoZ catalog, but it still has some outliers. That's actually already in the release paper for this catalog. There's an outlier rate of a few % or so. Now, if you make the assumption that these outliers are really high redshift galaxies that get assigned a low redshift PhotoZ, you can get shifts like this, just from a few % outliers. So this is just another representation here. This is the fiducial result. In brown is the result when you calibrate on the Cosmos 2015 PhotoZ. And actually in pink here, that's a calibration that's based on clustering redshifts, which I don't have time to talk about, but there you get a shift downwards, actually, which is interesting.
Henrik, is there any possibility of Cosmos 2015 could be something to do with the high-density regions of the catalog?
Yeah, we checked that, but I don't think so. This reweighting technique that we are applying should take out most of this density these density variations that you have in different lines of sight. So we think mean redshifts shouldn't change by more than 0.005 due to that, which is negligible, that level. So the next thing we did, and it was already shown yesterday, is we actually took the public DES catalog and tried to turn it around and do a spectroscopic calibration of the DES redshifts. That's what's shown here. So in dashed, you see the original redshift distributions that were published from the DES team. And in solid, you see what we find when we use spectroscopy. So spectroscopy from different fields like Z-Cosmos, VVDS, and in particular also Deep 2, which really gives you the high redshift edge that you need. And you see, especially for these upper 3 bins, that the solid line is consistently higher redshift than the dashed line. And everybody who knows a little bit about weak lensing knows if you increase the mean redshifts, you decrease your S8. And that's exactly what we're seeing. So here, these are the DES constraints with the original redshift distributions in dashed. And now if you use the spectroscopically calibrated redshift distributions, you shift down by roughly 0.8 sigma in S8. Contours are a bit bigger here because we use a slightly different setup with more conservative priors than DES did. Now, if you combine the two, you get this plot that was already shown, where you have a pretty clear separation of these contours from the Planck contours. Now, the question is really, what's the correct answer, right? Is the calibration with photometric redshifts better than the one with spectroscopic redshifts, or the other way around? I already talked about the systematic effects that you have when you use such a high-quality photometric redshift catalog as Cosmos 2015. There's certainly also problems when you use spectroscopic redshifts, and those have to do with the assumptions that I mentioned before. You need to cover the whole hypervolume in this high-dimensional magnitude space. If you don't do that, you get a bias, and you need a unique color-redshift relation. So this is something we're currently analyzing using self-organizing maps, basically checking whether our color space is fully covered by our spectroscopy, and so far it looks like it really is. So in that sense, we're trusting the spectroscopic calibration somewhat more, but certainly this will be checked further in the future. So to summarize, this talk is supposed to be about challenges. I think the astrophysical challenges are really important for the stage 4 surveys, but I don't think they're one of the major systematics currently in the stage 3 surveys, the intrinsic alignments and the baryon feedback. The shear calibration is something I haven't talked about, but also that is under better control at the moment, I think, than the redshifts. So the redshifts is really what more and more people are most worried about nowadays. So I mentioned the outliers and the bias that you can get from a PhotoZ catalog, and I mentioned the magnitude space coverage and the uniqueness of the color redshift relation when you calibrate with spectroscopic redshift as potential issues. Now, the interesting point is, even if you don't cover magnitude space fully, even if the color redshift relation isn't unique, I think all of these effects would rather lead to an underestimate of your redshift and an overestimate of your S8. So if you'd correct for that, your S8 would come down even further. And that's why I think the tension we're seeing should be relatively robust, even if we have some of these systematics still in there. I didn't have time to talk about clustering redshifts, but there's a nice complementary probe which makes completely different assumptions, but is currently not as mature as these other techniques. So there's still development work needed to actually get this to the same level of systematic accuracy. All right, my time is almost up, so let me summarize. We see some mild tension between some of these cosmic shear experiments, like the kids' Viking analysis, like the recalibrated DES analysis that I showed you. And the big question is really, is there still some systematic error that we haven't understood? Will we know more about the redshift calibration a few years from now that invalidates these results? I don't know. I think that's the big question that we are facing right now. If all of this turns out not to be true, so if we don't find a systematic, then you should start asking the question, is lambda CDM in serious trouble? Is there a different model that could maybe explain what we're seeing there? And I think we're living in very exciting times. Really, in the next half year or a year, we'll get much better constraints on these things. So we are currently analyzing twice the data than the results that I showed you. And the survey is already finished, so next year we'll probably do 3 times the data. And the same is actually true for DES and HSC. They're also basically done observing with DES. HSC is still going on. And they will have much more precise constraints this year and next year as well. And I think it's really crucial to get this right, because we want to do cosmic shear with Euclid analysis T. If we don't understand the redshifts, there's no way we can exploit the statistical power of these stage 4 surveys. So it's extremely timely to get this right here. Thank you.
We have time for some questions.
Stop there. Thanks very much, Henrik, and not only because you said super nice things about our catalog, so I guess the question I have for you then is the effect you're seeing of the redshift calibration on Sigma 8 and company. Is that the same thing as what had been expected from the Euclid requirements?
From which requirements?
The requirements in the Euclid processing requirements. Is that dependence something that we had known about already in Euclid?
Yeah, so I think the baseline approach for Euclid is to use spectroscopic redshifts. That's why we're currently running these large programs on the VLT and KEC to actually fill in this hypervolume that I mentioned. Down to the Euclid depth, we definitely don't have complete spectroscopy. So the strategy is to really fill in those spots where we're still missing spectroscopy. Now about the catalog, let me just say, it's a fantastic PhotoZ catalog. The question is, can you use it blindly without correcting for these outliers? You could make some assumptions where these outliers are, and then this calibration would probably improve. Something we want to try out as well.
Thanks. Right. Okay. So my question is, with the addition of the Viking data.
The addition of Viking?
With the addition of the Viking data. Yeah. You eliminated high redshift tails in the low redshift tomographic bins. And my understanding from talking to Hank was that was not to do with the addition of the infrared data, but was to do with changes in the priors applied to the photo Z algorithm.
Well,
okay,
both.
Okay. Well, so my question
both
is,
have an effect on that. Yeah.
My question is, can you change your selection criteria to tune the photo Z calibration? To what extent can you play around with the selection criteria of the imaging data, okay, to, you know, reduce, you know, outliers and uncertainties in the
now that's a very good question. It's actually something we're currently looking into, which is related to this self-organizing map approach. So there are some cells in the SOM that aren't filled with spectroscopy. So we could just say we drop all the sources that lie in those cells and just calibrate objects which will give you new two-point shear correlation functions, so you would need to run your covariance again, but that's exactly something we're looking into. You could even be more aggressive and say I only take objects that are on cells where I have at least 2 or 3 spectroscopic redshifts for some redundancy, and then you better get the same result, otherwise it would hint at a bias. So yeah, we want to do this, probably coming out in the next month. But,
So first, thanks for the fantastic overview. So I have 2 questions. First, on the photometric redshifts, since you said that there are percent outliers that might shift the values, the cosmological parameters, I was wondering if you also tried to use Bayesian hyperparameters to check whether this somehow highlights any possible systematics referring to the outliers. And the second thing is on the intrinsic alignment. I guess, I don't know anything about intrinsic alignment, but I assume that you have a scale-independent intrinsic alignment, I guess. So for models beyond the lambda CDM, this is typically not the case, not necessarily the case. So I was wondering if you have any idea of how one could actually parameterize or include scale dependency in the intrinsic alignment if we actually want to test anything beyond the lambda CDM. Thanks.
Yeah, so about your first question about these hyperparameters to account for the outliers, I think that goes in the same direction as what I answered to Henry. You could make assumptions about what these outliers are, and then maybe you also, when you run your chain, try the data to self-calibrate itself. I'm not sure this would work. You would probably put some large priors on these hyperparameters and just decrease the precision of your results in the end, but it's something we haven't really tried yet. So it's certainly interesting because it has some appeal to use this complete PhotoZ catalog, but I think you have to face the fact that there are outliers. Now about the intrinsic alignments, we are currently indeed using a model that looks very similar to actually the shear two-point correlation function, just with an additional amplitude, so you also integrate over the power spectrum. And certainly you can think of more fancy models. I have no idea how this model would look like in extended cosmological scenarios. I haven't really played around with this. But yeah, there's clearly some work to be done there. But as long as we know that the intrinsic alignments are small, and we know this from several observations, and I don't think it has such a large impact. I mean, people are working on this. There will be a talk on Thursday by Maria Cristina Fortuna about intrinsic alignment work. And so we're trying to measure the intrinsic alignments to better inform the priors that we're using in our models. But at the moment, I just feel it's not one of my major concerns. It's not what I'm losing sleep over at night.
So do you have enough data so that you can look at different regions of the sky to see if there are any systematic changes in the residuals for sigma 8? Yeah, so so far our data set is relatively limited. I mean, in KITS we have 450 square degrees. DES is analyzing a bit more than 1,000 square degrees. So you could split it up. I don't think this has been done, at least not by us. Maybe DES has done that, I'm not sure. But certainly what I'm saying here is we're getting so much more data, and so then we're certainly in the regime where we can do this. I mean, we looked at the two-point shear correlation functions from the different patches in our survey, and there was nothing suspicious sticking out, not one of the patches, which all roughly have 100 square degrees or so, sticking out.
But I think we should do more on this in the future, also seeing what the CMB people do in that respect. It's very good lesson, I think.
Okay, one last question.
Okay, if I may, just a quick comment in support of your hypothesis that maybe the Cosmos photo-see calibration is a reason for the difference in the results. So just to mention that in 2010 we published a Cosmos cosmic shear tomography analysis, and one of the things we did there is to look at the galaxies which actually have indications for potential high redshift contamination, but which are assigned the low redshift primary photo-see, and we turned it around and looked at their shear signal and saw such a strong amplitude that it indicates that most of these galaxies are actually at high redshift. Okay, and my suspicion is that for future analyses, this contamination will go down once there are even deeper yes, and deeper near-infrared especially, I think will help a lot.
Yeah.
Okay, thank you.
No, that's a very good point, and yeah, that's why we cited your paper.
Okay, let's thank the speaker again. Okay, next we'll hear about cosmology with combined cosmic shear data.
Okay, testing. Yeah. Good. Okay, good morning, everyone. So I'm going to talk to you about our most recent work on combining DES and KIDS data. Thanks to Henrik's thorough introduction, I don't have to tell you what cosmic shear is, KIDS or DES is. So I can just get to the point. As Henrik mentioned, the strength of cosmic shear is that we can probe the matter distribution directly without having to rely on biased traces. But it doesn't mean that cosmic shear analysis is not complicated. Henrik told you about some of the complications that can arise in a cosmic shear analysis and how they can affect the results, in particular the redshift calibration. And here I'm going to tell you about some of the other ones first and how we can detect them and what the effect is, and then at the end show you the new result. Okay, so when we do cosmic shear analysis, as Henrik told you already, we mainly use these things called correlation functions. So we measure the shape of galaxies and then correlate the shape of two pairs of galaxies, take averages over millions of them, and then form these functions, psi plus and psi minus. There are advantages in using these functions, but they're not ideal for cosmic shear analysis, and I will explain to you why in the next few slides. So first of all, from a cosmic shear signal, we expect to get alignments of galaxies that are similar to these, and they're called E-modes, not to be confused with CMB modes. So you get tangential alignments around over-densities and radial ones around under-densities. But in principle, in your data, you could have other alignments, which are called B-modes, and these are these curly alignments like this. So these B-modes cannot come from the signal itself, but their main contribution currently is either just random noise realizations or systematics in the data. So we can use these B-modes to test the fidelity of the data, basically. But with psi plus and psi minus, that's the favorite statistics used for most of the cosmic shear analysis. Both DES and KIDS have used it in their primary analysis. You can't do that because they mix the E and B modes. Okay, so there are a number of statistics that attempt to separate these two modes. And out of all of them, Casabi's is the best one for these reasons that I have listed here. Casabi stands for complete orthogonal sets of EB integrals. And from the data, we can measure it using this equation here. So you have the correlation functions that you've measured. You take an integral over them between minimum theta and the maximum theta with these filter functions that make sure your Kusebis are either E mode or B mode. So they just do the separation. But what is nice about this is that this integral is finite, so you don't have to be able to measure the correlation functions over all ranges. So, and you define that theta min and max yourself. So they are, Kusebis are designed to separate E and B modes, but that's not the only thing they do. They do much more. First of all, they produce a clean separation, as they were designed to do. And their modes are discrete. So this n shows what mode you have. It goes from 1 to 2 to infinity. And because it's discrete, you don't have to worry about the effects of binning, which affect the correlation functions, both in the signal and the covariance. And then they are complete, which means that they don't lose any information, any EB information in the process of the transformation. And also they are efficient. So although the modes go from 1 to 2 to infinity, you only need the first few to capture the cosmological information. Their distribution is very close to Gaussian, which makes likelihood analysis easier. But that's more of a problem for correlation functions, which have less Gaussian distribution. And finally, they are less sensitive to small-scale information compared to correlation functions on the same angular range, which I will tell you later how this can help us in the analysis. All right, so I'm going to first focus on the B modes and what they can teach us about systematics in the data. So the thing is, we might measure B modes in the data. Well, what does it tell us? How can we know what it means? To answer that, we went and modeled several different systematics that can happen in the data, and then measure the B modes. But I'm going to show you only two of them here. So one of them is Psf leakage. So Psf, remember, is the point spread function, and it's the effect of seeing on the measurements. So say if you didn't model it quite completely, so like some bits of it were missing, that's called Psf leakage. And then the second one is something that that we call regular pattern or repeating pattern. This is a pattern that repeats over different pointings of your camera. So within a pointing of a camera, it might be random, but it repeats practically the same over all the pointings. So you get an image with this repeating pattern. One of the examples of this is if you have a CCD chip bias. So for example, here we have these, so these white rectangles, they're like one of the CCDs, and it has a higher bias, and it repeats all along the image. So let's see what is the B modes they produce. So this plot is showing the Kusebis B modes for the first 20 modes. And the there's science verification data on top of it, plotted on top. So this is the red ones are the B modes measured from DES SV data. And the blue ones are the signature of the Psf leakage, and the black one is the one for regular pattern. Now, if you focus on the low end here, you see that DES SV data shows a signature similar to the Psf leakage, and at high end, it looks similar to regular pattern. By the way, I should note that the B modes in the SSP are significant, so they're not consistent with 0. But we're not interested in B modes. We want to do cosmic shear and the signals in E modes. So now the question is, how do these affect the E modes? To answer that, let's look at this plot. So this plot is showing a compressed cosmic shear signal versus S8. So S8, let me just remind you, is a combination of sigma 8 and omega m. that cosmic shear is mostly sensitive to. So there are 3 lines here. So these are theoretical predictions for the cosmic shear signal. You can see that as S8 increases, also the cosmic shear signal increases. We have to see what is the effect of the systematics on the signal. We added them to mock data and then measured the signal for them. First of all, let's look at the red points. The red points are showing the case where you don't have any systematics in the data, so it's a cosmic shear signal, pure cosmic shear signal. And you see that they align with each other nicely and give the same as 8. And then we have, if we add Psf leakage or regular pattern to the data, then we get an overestimated S8, as you can see here. So this is Psf leakage, this is regular pattern. Which means that if these systematics exist in your data, you're going to get an overestimated S8, or in other words, this is only going to make the tension larger with Planck, not smaller. So we can't explain it with these kind of systematics. All right, so now I'm going to transition to combining DES and KITS. But before doing that, I have to tell you a few things that we did differently to DES. So first of all, the DES-SV data had B mode, so we had to check that DES year 1 data doesn't. We did that after it became public, the data became public in this paper here. Here the DES year 1 has 2 catalogs, meta-calibration and IM3 shape, which measure the ellipticity in different ways, but you don't really need to know what these are. All you need to know is that the meta-calibration is their primary catalog, and it has more galaxies and more statistical power. So the plot here, on this side, we can see the B modes for the year 1. The blue ones are the meta-calibration, the main primary catalog. And you can see that they are pretty much consistent with 0. And then on this side, this is just the E mode measurement. So this is the cosmic shear signal. And so I'm showing the first 20 modes here. But for the cosmic shear analysis, we don't need to use all 20. So we just use the first 5 where the signal is. The rest of that basically goes to 0. OK, so that's one difference is we're using Kosevis. Yep. And then the next thing is the question of which angular scales can be used. So Henrik showed you that baryon feedback can affect the matter distribution. So baryon feedback, for example, with AGN feedbacks, you push the matter out of the dark matter halos. Effectively, you decrease the matter power spectrum on small scales, basically. And these small scales, small physical scales, translate to angular scales, but in a non-trivial way. So for the DES year 1 analysis in Troxel et al., they didn't model baryon feedback, and instead they decided to put scale cuts on their data to basically be kind of insensitive to the effects of baryons. Here, we're not going to do that, and I'll show you why. OK, so let's see what is the effect of baryons on these different statistics. First of all, here I'm showing a plot of integrands for psi plus, psi minus, and Kosevis. So these integrands, what are they? So when you want to do a prediction for these statistics, you take an integral over the 2D power spectrum. And this is the integrand for that. So each of them have their own kernel. For example, psi plus is J0, psi minus is J4, and Kosevis has their own weights. So first look at the first 2 plots here. The red curve is showing the integrand for 0.5 arc minutes. and then the blue is for 10, and then the black one, the dotted one, is for 300 for both of them. What you see here is that the psi plus takes a lot of power from different L modes. Like even for 0.5, you have a lot of power from low L modes here, going to very high. And then for psi minus, you see that the kernel is much more compact, but it takes a lot of information from high L. And these ranges, like 0.5 and so on, are usually excluded from the analysis because of this reason. And then finally, we see for Cosmology, we see the kernel for modes 1, 2, and 5. Remember that we're using only the first 5 modes for the analysis. For the same angular range, so 0.5 to 300. And you see that it is much more compact, and it doesn't really care about anything that's happened here or anything that's happening here. So it's insensitive to these scales. And now this very nicely connects to this other plot that's showing the sensitivity of these statistics to baryon feedback. So on the top two are psi plus, psi minus again, and the bottom one is Cosmology. And here we're comparing 3 baryon feedback models: high feedback, medium feedback, and low feedback, with dark matter only model. So if it was on 0, then there is no baryon feedback, basically. And you see that psi plus and psi minus are affected in a similar way by psi minus more than psi plus, because it's taking more power from these scales. And they both, for both of them, you get less correlation, basically, because of baryon feedback. These are the scale cuts used for by KB450, Hildebrand et al., and Desir 1, Troxel et al. And then now, if you look at the bottom plot with Cosmology, you see that the effect is very small. And you can see why, because it's not taking anything from there. OK, so we checked that the data is fine. There is no B modes. And we're not sensitive to baryon, so we don't need to do the same scale cuts. So we're going to take the larger scale range of 0.5 to 250 for DES, and 0.5 to 300 for K450. OK, so now this is results from a paper in prep, going to come out probably in a month or so. Here I'm showing S8 again versus omega m. The small contour is Planck, primordial Planck, and the big gray one is the original analysis of this year 1. We did the same analysis but with Cosmology and the larger angular range. So exactly same setup and everything, redshift distribution and so on, and we get the magenta contour. So you see that it's right on top of the gray one, but it's much smaller because we're using the larger range of scales. But we wanted to combine the two, so we had to put them on the same footing. And if you do that, if you use the same setup as was used in kids, you get the cyan contour. So you go from here to here. And then there is the important question of the redshift calibration. So now if you use the direct spectroscopic redshift calibration that Henrik told you about, you go from the cyan one to the orange one. And this is consistent with the results from psi plus and minus. OK, now that they're on the same footing, we can combine them. Here we have the cosmic shear banana. Sigma 8 versus omega m. The green contour is the analysis of KB450 with Cosmology. The orange one is the same orange one I showed you before, but in this parameter plane. And the combined one is pink here. Planck is again shown in red, small contour. And because we have more statistical power, we also get more tension than the paper that came out on Monday. I'm not telling you the exact value of the tension because this is preliminary results, but if you wait 1 month, you will see the exact value. Okay, so some final remarks. So I hope I convinced people that CosmGold is a good method to use for cosmic shear analysis. We can do a consistent cosmic shear analysis because you can simultaneously use the B modes to test the data and the E modes for the analysis itself. The code has been integrated with Cosmosis, and it is available on request. And then finally, tension. Yes, you should get excited.
We have time for 1 or 2 questions.
Thank you very much. This is very interesting. So as I understand, the CosmGolds give you a better way to separate scales which are affected by baryon feedback than with the correlation function. My question is just, is this also using the same tomography, so 5 bin? So basically you have 5 CosmGolds in each tomographic bin to get these constraints? Or?
No, the 5 modes, you have 5 modes per pair of tomographic bins.
Per pair, okay.
Yes.
Thank you.
You showed us 2 ways how one can induce B modes in the signal, and both of them enhance the tension or give you a smaller S8. And is this generic, or is this just for the 2 cases which you were showing us?
That's a good question. So we modeled loads of different ones, and it seems like it is pretty generic. It's quite hard to model a systematic that decreases the signal, basically. They usually add power to the signal. There are ways to do it, but they're not very natural systematics to add, basically. So anything that you can think of that could exist in the data generally increases the signal. Yeah.
Other questions? If not, let's thank the speaker again. Okay, we're going to change gears now, and we'll hear about cosmology with peculiar velocity surveys.
Okay, good. Can everyone hear me? Yes, good. Hello, yes. So my name is Colin Howlett. Today I'm going to be talking about cosmology with peculiar velocity surveys. And yeah, a large part of this work is actually done by one of my students and in collaboration with a bunch of other of my collaborators in Australia. Before I get onto the science, apologies, but I'm going to share some in real life spam. So we have some postdocs that we're hiring at UQ, which some of you may be interested in. So these are 3 to 5 year on the very broad topic of understanding dark energy and dark matter with next generation data sets. Here's some examples, but it's open to interpretation. And so there's potential to get involved in some of the surveys we've heard about this week so far. And this will be on the job register soon, but it's out of cycle, so I thought I'd let you know. Within the next month or 2, and so please talk to me if you want more info. Okay, so now onto the science. So my goal for today is to tell you about peculiar velocities and how they have the potential to be one of the best cosmology probes at very low redshift. So this is probably one of the lowest redshift talks we'll hear this week. But how there's quite a lot more work that needs to be done to understand how to use these and how to control for various systematics in these as well. So firstly, I'll tell you how do we measure peculiar velocities. This is a somewhat niche area, so I'll explain what these are. Then how they can be used for cosmology. I'll give a couple of examples, including constraints from current data sets. So for instance, looking at the bulk flow, which is the average bulk motion around us, and comparing that to the CMB dipole and the predictions from lambda CDM. And also measuring the correlations between velocities using either the velocity or momentum power spectrum, which can be used as a test of gravity. And I'll show you some forecasts for future data, and I think hopefully try and back up that claim at the top. So just as a basic introduction, so I hope I don't have to tell you all that galaxies are moving in two ways with respect to us. So one of those is the expansion of the universe, the Hubble flow, and the second is motions due to our local large-scale structure. And some people yesterday were actually asking me about whether or not local voids can explain the H0 tension. So I've included this diagram here. This is a map using pure velocity surveys of our local field, and you do see we are indeed on the edge of a local void, but it's rather small. So the current pure velocity data says it's only on the order of, say, 10 to 20 megaparsecs over H, which is not enough to explain the H0 tension. Overall, though, what this means is because the galaxy is moving with respect to us in two ways, galaxy redshifts are not perfect proxies for distance. So this is very annoying for measuring distance. If they were perfect proxies, I think all our problems would be solved. But what it does mean is that they are great for testing gravity. And so what we can do is if we can get measurements of the velocities, and we can also get measurements of the overdensity, we can constrain these parameters here, which are cosmological parameters and of interest. And in particular, this is the growth rate of structure, which has got strong predictions from general relativity. You can also predict it from various other modified gravity theories. And in particular, in GR, it's got quite a strong time and scale dependence, which is to say that it should evolve only with a matter, and there is no scale dependence at all on linear scales. So typically, pure velocities come into play in redshift space distortions. We've heard a little bit about this today. And that's to say that when you measure the galaxy clustering using measured redshifts, you've got this contribution from the true redshift, which is due to the Hubble expansion of the universe, but you've also got this contribution from peculiar velocities, and that introduces an anisotropy in the redshift space clustering of galaxies, which in this case manifests as a squashing of spherical overdensities along the line of sight, and then in the center you get nonlinear motions, such as fingers of God, which introduce this elongation along the line of sight. And the benefits of redshift space distortions, and the reason they've been used really quite widely over the last 20 years to constrain cosmology, are that redshifts are extremely easy to obtain, or relatively. We now have surveys on the order of millions. DESI and Euclid are going to go on the order of tens of millions. However, the clustering does depend on unknown astrophysics, in this case the galaxy bias, and it's also, as we heard earlier today from Lardo, cosmic variance limited at low redshift. Which means that there's a limit to how much information we can obtain, even with surveys where we have tens of millions of galaxies. An alternative is using empirical distance measurements to extract this velocity separately. So this velocity encodes gravity, and so by extracting this separately, independent of these two redshifts, we can test gravity directly. And there's a number of ways we can do this. Really what you need is a measurement of the true redshift, so the true distance to a galaxy. You can do this with the Tully-Fisher relation, so that's what's shown here. So this is a relationship between basically the rotation velocity or velocity dispersion of the galaxy at Vmax, which here is measured from a H1 survey, and the true brightness of a galaxy. And in this case, the peculiar velocity encodes the scatter in this direction, so at fixed Vmax. You can also use the fundamental plane, which is a bit more complicated to show, because it's three-dimensional, or you can also, of course, use type 1a supernovae, which give you the distance modulus, which is also a measure of the true redshift. We may also, in the future, be able to use gravitational waves for this. They also give you a true measure of the distance. And so what this does is it gives you a direct measurement of the velocity field, which is independent of galaxy bias. It traces the matter flows directly. And it can be combined with density field measurements to overcome the limitations of cosmic variance that we will see in the future with things like DESI. Two other examples, as I was saying earlier, this is the fundamental plane. For reference, the peculiar velocity effectively encodes scatter along the effective radius direction. It makes galaxies appear larger or smaller than they would if there was no peculiar velocities. And for supernovae, it's effectively scatter about the Hubble flow. So it's a scatter in the residuals of the distance modulus, mainly at low redshift. At high redshift, you have other effects which come into play, such as lensing. And so another way we can recast this is we can say, given our distance indicator, we can infer the true distance. Given the measured redshift of the host, we can get an inferred distance, assuming some cosmological model, and then the offset between those two is directly proportional to the velocity. And so these surveys are currently limited in terms of number, but they also have quite a lot of intrinsic scatter, as you can see here. However, we do have a somewhat large sample currently when you combine all data sets that people have been working on for the last sort of few decades, in fact. And then in the future, this is going to kind of explode, and we're going to have way more galaxies than we will know how to deal with. And so at the minute, there are around 20,000 total peculiar velocity measurements. However, these have varying selection functions and reliabilities. It's quite difficult to combine them. Nonetheless, I'll show that these can produce quite good cosmological constraints. And so that gives us hope for the future. So one of the first things we can do is look at bulk flow and shear, which is effectively the second order moments in the velocity fields. I'm only going to really talk about bulk flow here in this talk. And so what that is basically just measuring our motion with respect to observed galaxies in the CMB. We've done some constraints using a combined sample of around 19,000 galaxies now. So this was published in a paper this year. Here I'm showing effectively the bulk flow. So this is the bulk velocity with which we are moving with respect to the CMB. And then here we have radius. And you can see that really the takeaway message from this is we can get really quite exquisite measurements now of our local bulk motion. However, if you then try and compare these to lambda CDM, which is shown by these curves here, so this blue one is the 68% variance for you might expect in lambda CDM. This is the 95% variance you might see in lambda CDM. Really, the kicker is that lambda CDM predicts really quite a wide range of bulk flows in the local universe, which is to say that you could plonk us down anywhere else in the universe, and you might expect any bulk flow to be measured within here. And so really, cosmic variance is a limiting factor for these kind of measurements. And so what we want to do in the future is you really need to push to larger depths while still maintaining error bars and systematics, which will allow you to keep these same sort of measurement errors. When you measure the bulk flow, not only do you get a measurement of the amplitude, so the speed of the bulk flow, you can also measure the direction. So I thought I'd put this plot in because it mentions the CMB. So here we have marks as across the direction of the CMB dipole. I think this is measured by Kobe Firas, I think. Here we have a bunch of different measurements of the bulk flow measured from our low redshift surveys. The green measurement here is that sample I was showing you earlier of 19,000 galaxies. And the takeaway message here is that there's some sort of misalignment between the direction of the CMB dipole and our local measurements, which again would argue that we need to push to larger distances in order to really work out whether or not our bulk motion is aligned with the CMB dipole, as we would hope. So at the minute, there's no statistical significant deviation from lambda CDM predictions, but the lambda CDM predictions are allow for quite a wide range of values. And so what we need in the future, so one of the challenges we need to come up with is more constrained predictions or greater measurement depth. But we need to do that while also ensuring good control of systematics. And I'll just point out what I mean here. This measurement here, S16, uses the same data as this blue point here. And all we've really done is we've reanalyzed the data and tried to control for systematics in the survey selection functions better. And you can see these can make a huge difference, not only in terms of the amplitude I was showing earlier, but also the direction that you might expect the bulk flow to be in. Another probe we can look at is velocity correlations. And so these are correlations between galaxy velocities and positions on the sky, and we can compare them to theory. So I'll show this equation again. So here we have the velocities that we're measuring. You can also measure densities at different points in the universe. But what you can do is if you correlate velocities at two different points on the sky, you can write down what we call a velocity power spectrum. So this is the velocity power spectrum on quasi-linear scales. So here you've got the matter power spectrum here. Here you've got some term which accounts for nonlinearities. And the kicker really is that this measurement depends on the growth rate on linear scales, uncontaminated by galaxy bias, unlike with redshift space distortions. So this is what we've used to constrain the growth rate of structure using some of our data sets. So this is a fit to the two-mass Tully-Fisher survey, so 2MTF. This contains only about 2,000 galaxies, very low redshift. And this is not a direct measurement of the clustering, but it's an inference of the growth rate of structure by basically looking at the maximum likelihood probability of all those velocities that we've measured. And the takeaway message here is that the constraints using only 2,000 peculiar velocities are only about 1.5 times worse than the full 6-degree field galaxy redshift survey, which contains about 70,000 objects. So the takeaway message here is that a peculiar velocity target, if you can do it well, is worth many, many redshifts. But one takeaway message from this as well is that this method is very slow. For 2,000 galaxies, it was quite tough to do. For future surveys, this is going to be an issue when we start having tens of thousands of objects. You can also fit these in K-bins. So here I've done the same inference, but instead I've split into K-bins. And you can compare to the expected shape of the power spectrum from GR, and you can look for evidence of scale dependence in your growth rates. and we find no evidence of scale dependence in our 2 MTF results. But that's not to say that with future measurements we wouldn't be able to do better. We can also measure what I call the momentum power spectrum. So that previous method was not a direct estimate of the clustering, but it was rather an inference just by looking at the distribution of the actual velocities on the sky. What we can do instead is we can come up with a way to estimate the velocity power spectrum directly by placing all the data on a grid, doing a Fourier transform in the same way that you might do a redshift space power spectrum. So this is almost exactly analogous to, for any clusters, galaxy clustering people in the room, the FKP or Yamamoto density power spectrum estimators. And they share many properties, so you can add, you can account for shot noise, you can account for, you can calculate analytic covariance, you can normalize them in the same way. And you can calculate an optimal weighting. And so this is something that's very promising for future surveys. What I'm going to show here are measurements of the monopole and quadrupole, so to the anisotropic momentum power spectrum, measured from some mock peculiar velocity surveys I generated. These are next generations. They involve on the order of 150,000 supernovae, so they're quite accurate distances, which is rather optimistic, but is possible with LSST, or LSST combined with some of the other measurements that we're going to get in the future. And you can see that you can get really quite accurate measurements of this momentum power spectrum, both spherically averaged and anisotropic. And on linear scales, one thing to point out is that this depends purely on the velocity power spectrum. So that's this dashed line, which you may not quite be able to see at the back, which then extends down here. And so on linear scales, this is also a pure tracer of the growth rate of structure. And so it's a pure measurement of a pure test of gravity. This full model was done using perturbation theory, so there's also higher order terms which come in here, but they can also be included in the model relatively easily. As an example of the constraints we might be able to get, so yeah, like I said, these were 150,000 peculiar velocities. I generated a bunch of mock catalogs, so this is just fitting to the average. You can see that here I'm showing the growth rate of structure constraints from those mock catalogs. So this is not a Fisher matrix forecast, these are full fits as you might apply to data. The black contours show the measurements when we only use redshift space distortions to constrain these, so just using the density field. I fit the first 3 multipoles, so monopole, quadrupole, hexadecapole. And then if you add in the momentum power spectrum as well, you get a significant improvement in the growth rate measurements by nearly a factor of 2. One thing to note is that there is a bias in the recovered F sigma rate. So this blue line is the input to the mocks, and that's almost certainly a result of modeling systematics, which again, if you want to use this in the future, is something we're going to have to start looking into. And I'll list some of those in a minute. But the take-home message is that there's significant improvement when adding velocity field information on top of the density power spectrum. So we did apply this to data. These are the constraints in the data. These fits, regardless of whether what it looks like here, are actually very good. The chi-squared is very good for these fits. You shouldn't really do chi by I because all these measurements down here are highly correlated. But here we fit to the combined 2-mass Tully-Fisher and 6-degree pure velocity surveys, so that's 10,000 objects. And current measurements are not really at the level where we have to worry too much about modeling systematics, but we will in the future. And so these include things like wide angle effects, nonlinearities, velocity bias, and there are a lot of the same things we have to start worrying about for redshift space distortions with things like Euclid and DESI. And so the hope is that we can piggyback on a lot of the ways that these problems are being solved. This is now a plot of the growth rate of structure from a sample of surveys. Apologies if I've missed anyone obvious out. But this is just to highlight our new measurements. So these are comparable to some of the constraints we're getting with large-scale structure surveys at higher redshift. But these ones are a much lower redshift where you've got a greater opportunity to disentangle different predictions for the growth rate of structure. And one thing I will highlight here is we did a fit to all these data points naively, so we didn't fully take into account the correlation. So this is just to guide the eye. It's not a result in any significant sense, but there is, as people have pointed out in the past, some hints of a slightly preferred value of gamma, which may, in the future, get stronger or go away. So in the future, we're going to increase the total number of pure velocities by quite a significant amount, so over an order of magnitude. Current surveys have about 20,000 combined. With a Type N galaxy survey, we're expecting to get 50,000 fundamental plane objects. With Wallaby, we'll get about 30,000 Tully-Fisher. LSST could have up to 200,000 Type 1a supernovae, although that's somewhat questionable at the minute. It's also possible that we could get fundamental plane galaxies with the DESI bright galaxy sample, although I haven't looked into this, and so I don't know what kind of numbers we might get there. And so combining these with galaxy redshift surveys at the same epoch will improve our test of gravity enormously. But we do need to learn lessons from other cosmology measurements and how we can learn to deal with large samples and systematics, in particular where we can't look at each galaxy individually, which is what we've often done in the past with these sort of small samples. Here I'm just going to show some forecasts from the Taipan Galaxy Survey, which combine the two. So peculiar velocities and redshift space distortions. You can see the error bars we're expecting from just statistical error bars from the Fisher matrix forecasts are extremely small at these sort of redshifts. So these will have potentially a lot of constraining power, but we really need to start looking at the systematics that could affect these, especially when combining positions and velocities. And then, although rare, type 1A supernova are much better than fundamental plane. Fundamental plane distances have typical errors of 20%. With improvements in supernova, we could expect up to 5% distances with LSST. And so just as a sort of motivator for people to start thinking about this in the future, here I'm showing some Fisher matrix forecasts I did for the DESI Bright Galaxy Survey. So this has about 700 targets per square degree. And I've split these into very narrow redshift bins, but these are the kind of constraints on F sigma 8 you'll be able to get on all these very narrow redshift bins. And now if I switch to the hypothetical and rather optimistic scenario of having peculiar velocity measurements for all LSST detected supernovae, these error bars shrink dramatically. And although this is rather optimistic, it's not easy getting a supernova peculiar velocity, even in the area of LSST. It's worth noting that the number of targets here is much, much more than the number of redshifts we're getting. So this really does highlight just how useful a single peculiar velocity can be compared to quite a large number of redshifts. So just to switch back and forth, this is about 700 targets per square degree. This is 120. And so the difference there is really quite striking. However, there are still lots of unknowns with this that we need to look at if we want to do this well. How many supernova will we actually get? What are the effects of supernova systematics on growth rate measurements? And also more of a sort of philosophical question, which is how do we deal with transforming what is typically an astronomy field, so direct measurements of pure velocities, into something which more closely resembles modern cosmology, which is the kind of thing we're dealing with these large redshift surveys, with Euclid, with weak lensing surveys and stuff. Okay, so just to conclude, I hope I've convinced you that peculiar velocities have potential to be one of the best cosmology probes at low redshift, but we still need to understand how to use them and how to control for some of the systematic effects in there. They give good constraints from current surveys, and they'll give hopefully groundbreaking constraints in the future when we increase the number of peculiar velocities we have by an order of magnitude. But there's still lots of work to do. And so I'd be interested in hearing other opinions and ways to get or use this data and tackle some of the challenges while I'm at this conference. Thank you.
We have time for a couple of questions.
There may be an obvious no-go here. This might be something everybody already knows about, but have you looked at non-gravitational changes to the growth rate? So I have in mind just neutrinos going from relativistic to non-relativistic. Would that be distinguishable, or do you need to go to higher redshift?
So I haven't looked into this at all. I think if someone wants to come along and do a Fisher matrix forecast, it's very easy to do these kind of forecasts. Really, the question is whether, so most of the changes due to neutrinos tend to be on nonlinear scales. So I'm not sure how this would manifest in changes in the growth rate, for instance, in the peculiar velocity. Velocity. Yep. Right, yeah, so that's something that if you can calculate the growth rate, the effect of neutrinos on the growth rate, you can certainly start looking at that in terms of both the forecasting for future surveys and also trying to extract something from current data without any issues, I think.
So you wrote down essentially the linearized continuity equation a few times, but notice in your galaxy velocity cross-correlation measurement, also the momentum measurement, you kind of already shown that the delta V term, which is you neglect from linearize the continuity equation, is probably non-negligible in the scale you're probing. So I wonder, in practice, how you deal with that term in the modeling side?
Yep. So in fact, so the momentum power spectrum is probably best shown here. Yes, there is this significant nonlinear term. So momentum, how I defined it, is 1 plus delta in brackets times V. So that means obviously you've got a delta V component in there. And so you end up with what we call the delta V power spectrum. However, you can model this using perturbation theory. This model here is I think I took from a 2012 paper, which just uses standard perturbation theory to calculate all the relevant terms. And it also includes, first linear bias. You can also include second order bias. And you can include these as nuisance parameters in the fit, which is what I've done here. So the total fit here, I think, included 7 parameters, one of which was F sigma rate, but there's a couple of galaxy bias parameters, some nonlinear velocity dispersions. But this is something which has been tested a lot with redshift space distortion. So we've got quite a number of models that people have tested on mock catalogs before they've applied them to data. That hasn't been done anywhere near as much with these sort of surveys. And so that's something I'll be very interested in talking to some of the theorists and people who are interested about in the future is what models are best to extract the growth rate constraints from these sort of measurements.
Okay, let's thank the speaker again. Okay, the last talk before lunch, we'll hear about combining RSD and lensing around peaks and voids.
Okay, good. Well, thank you. Thank you for staying awake for the last talk of the morning section. So just to echo some of the calls in the first talk by Gigi and Lado, there's essentially a need perhaps to go beyond the conventional two-point statistics, namely correlation function or power spectrum, and look for some slightly orthogonal alternative probes for large-scale structure and trying to see if it's possible to pull out information or more information by this alternative method. So this is illustrated, but the title where is here I'm advocating essentially kind of an old topic now, which is to combine redshift space distortion with weak lensing over the same sky and looking particularly around these peaks or clusters and voids and see if we can learn anything about cosmology. So let's, as I said, this is an old story. Let's remind ourselves what redshift space distortion is based. Is essentially looking at, if you look at this patch of overdense regions in the universe, the infall velocity would drive things to appear squash along the line of sight as we look through these overdense regions like clusters. And this real space to redshift space mapping allow Kaiser 1987 to write down the mapping between the redshift space power spectrum versus the real space power spectrum. And if you just simply reorganize these terms, you realize that the limit of redshift space distortion that allow you to constrain the growth is essentially constraining these two quantities, namely some combination of the linear bias, which is degenerate with the linear growth rate f, and also some combination of this growth rate factor f and the growth parameter. So we also know that this equation essentially is only valid really at the very, very last scales when linear theory applies. Whereas on the very large scales, we are fundamentally limited by the size of the survey, essentially the volume. So that's fundamentally limited by cosmic variance. So to break through this cosmic variance limits, back in 2009, McDonald and Seljak came up with a pretty revolutionary idea to advocate this so-called multi-tracer redshift space distortions over the same volume. So essentially, the idea is with galaxies of different biases, they are tracing essentially the same underlying perturbation of dark matter. So if you then take the ratio of these perturbations for galaxies of different biases, then the ratio measurement would be free from cosmic variance because they are in phases, these perturbations. So this diagram shows you some Fisher forecast we did many years ago. So the y-axis is showing the fractional error for the constraint of the growth rate, the growth functions, the growth parameters, versus essentially the depth of your survey. This is on a fixed sky area. And so from the left to right is mimicking the case where the depth of the survey is going deeper and deeper. As you can see, the standard redshift space distortion, where you exercise a single tracer over this field, it will be limited by the cosmic variance line here. At some point, no matter how much more denser you increase your survey, you will no longer gain in constraining the growth. So this is the combination of F times G, where G is the linear growth factor. Whereas if you exercise multiple tracer redshift space distortion, if you have a wide range of halos or galaxies of different biases to exercise this, then you will break this limit and can gain significantly more in constraining the growth. So fundamentally, if we then were able to somehow have a prior knowledge on the galaxy bias, then you can immediately also go down to this line, which is some sort of redshift space distortion plus the prior knowledge, perfect knowledge of galaxy bias. And that also allowed you to have separate constraint for F and G independently. So this is very charming, and that drive a whole group of, a large group of people go and forecast for what you may gain by placing two surveys. Essentially, one is lensing, another one is a spectroscopic redshift survey over the same sky, such that you can use the cross correlation between lensing and the spectroscopic redshift sample to measure the galaxy bias. So the crucial here is to use this essentially the off-diagonal part, characterized the lensing measurement, and galaxy is the galaxy over density region, galaxy over density field to have a constraint on galaxy bias. So up to that, this list of maybe a complete list of literature, most of the work has been done with feature forecast and also in forest space. So in this in this preliminary work, I'm trying to advocate like what we can possibly gain by shifting our essentially the observers into centering ourselves around peaks and voids, and cross-correlating these peaks and voids with the rest of the galaxy field, and then exercising the measurement of lensing over this field, and also have some model prediction for the redshift space distortion around these peaks and voids, and see if we can gain any more information. So I would just list a few charming or goals or questions trying to achieve, which is, by the end, hopefully it will convince you that this is, will allow us to go to explore nonlinear dynamics and then explore information from the small scales, and thereby perhaps gaining more information. And because we are exercising lensing plus redshift space distortion, the cross-correlation of these two would allow us to measure the bias directly. So we may not need a bias model, even at the very small scales. And also, I'll show perhaps we also don't even need the initial shape of the power spectrum. We don't necessarily need the initial conditions. So, but the limit is we're going to test merely just the dynamics under a assumed cosmology. And for void particularly, we know that the perturbation around them would be order of unity or subunity. So perhaps the dynamics there will be slightly simple to model. So what we need to exercise this, obviously you need a lensing and redshift survey over the same sky. And then assuming that lensing gives us the measurement for the true density field, then what we need is a model that allows us to predict the velocity around these peaks and voids, and thereby to further allow us to predict redshift space distortions, and then to contrast with the data. Right. So this is actually not a new thing. So it's been done to a great extent in the literature, but this is certainly not a complete list. But especially for clusters. So these are essentially a bunch of cluster, as labeled in red, cluster mass cross-correlation as measured from simulation. So as you can see, the profile, essentially, this is the mass profile, but not around clusters or peaks, but up to very large scales. And also these blue curves are essentially the cross-correlation between voids and the rest of the mass field. So it's underdense. So the idea is now, by splitting up the density field into a bunch of local densities of different value. Essentially, if you look at this diagram that illustrates the late time one dPdF of the density field, and we've chopped them up into various of density bins, and then we cross-collate these various of density bins with the rest of the field. And we're asking the question whether or not these would give us some cosmological constraint, or whether or not further this can gain us more information than if you cheat the entire density field equally perturbatively and then do the conventional two-point correlation function or power spectrum. I think without doing that, perhaps the answer is kind of obvious, because if you look at this distribution at a late time universe, is highly non-Gaussian. And then by splitting things up into this way, we were perhaps, in a way, be able to retrieve some of the information from the tails. Whereas if you're exercising the two-point statistics, then essentially you're calculating the volume, so the variance of the field. Therefore, you will probably lose some information because of this non-Gaussian nature of the field. Right. So remind ourselves again, this is a picture of redshift space distortion around clusters. It will appear squashed. And if you, from the density field, if you stack many of them, it will eventually get into the stage where the stacked cluster profile will be close to spherical. And you can then make a prediction for the velocity field, and then you have a prediction expectation for the redshift space cluster Gaussian cross-correlation function, as shown by this paper. So for voids, for this, with the same logic, you can kind of expect that it's a slightly underdense region compared to the mean. Therefore, the peculiar velocity will be pointing outwards. And it's actually non-trivial that you may not expect actually the void would appear elongated in redshift space. In fact, even if you write down the linear theory expectation, it will be actually be contributed. The redshift space void Gaussian cross-correlation function will be determined by all these bunch of fields, including the terms, including the density and the velocity and the gradients of the velocity. So in practice, well, you can verify this by go about to measure the void Gaussian or the void halo cross-correlation function in simulation, and you can also subtract the real space version of it. You can see the distortion pattern actually appear to be slightly squashed around the center, and then slightly elongated further out. So it's a pretty profile-dependent thing in terms of the distortion pattern around voids. So just because this is, in terms of void, it's a slightly maybe a non-mainstream stuff. So let me illustrate what we're going to do in modeling its peculiar velocity. So the idea is to employ spherical dynamics. So this is mimicking spherical collapse, but then we just set up the initial condition to be slightly underdense, and then let the whole system to evolve. And you can see that the essentially peculiar velocity is pointing outwards. Therefore, this top hat, inverse top hat, start to expand, and then matter start to accumulate at the edge of the void. So essentially, before shell crossing occur, the initial density, a whole bunch of initial densities, is uniquely mapped to the late time density. So this simple argument allowed us to essentially use the spherical dynamics, spherical model, or spherical collapse, or spherical expansion to predict the peculiar velocity. So essentially, what we need to do is to, from some late time observation from lensing, which is the density field at the late time, the spherical density field either peaks or voids at the late time, and then we go about to find its corresponding initial density given a cosmology. So this is illustrated here for the case of void. This is some late time density profile around the center of a void, and then you can essentially interpolate back to its initial condition given an assumed cosmology. In this case, we're just illustrating the dependence on omega m. And then you go forward to have a full prediction for the peculiar velocity around these spherical regions. So this is, again, omega m dependence for the same observed lensing void, the same void observed by lensing, but then correspondingly, there will be a dependence on omega m in terms of the amplitude of the peculiar velocity. So this is the density and the velocity is essentially the two pieces of ingredient that you need to predict for redshift space distortion around these spherical regions. Again, this is illustrating the case for void. And and then you can contrast this or confront this theory prediction with your observation from the 3D redshift survey over the same sky. So this is the financial model cosmology that you can expect from this spherical model, and this is the same true matter density, but with different cosmology, and that give you a different peculiar velocity, and thereby you can see by eye that the redshift space distortion pattern looks completely different. And this is where the constraining power comes from. So with that, we can essentially set constraint for a bunch of parameters free from the initial condition. Bear in mind, we're starting from observation of lensing, and we end with a prediction for RSD, and then also compare it with observation. Therefore, we are essentially free from the initial condition. There's no assumption about the shape of the power spectrum or correlation function from the initial condition. We're essentially just testing the cosmological dependence of the spherical dynamics with this exercise. So here we're setting constraint for some sort of deviation. This G factor is characterizing the deviation from the gravitational constant, and this omega m, omega lambda diagram for a few gigaparsec cubed volume. And just to illustrate that things work, and a highlight of this exercise, of the charming thing about looking at particularly underdense region, is that if you look at this spherical evolution equation, it's essentially governed, the evolution of the radius is governed by two things. One is the mass dominated term, which is related to omega m, but also related to how much mass within that radius. And the second term is essentially the background dark energy term. So by looking at the slight center of our voice, which is the case indicated by this the sine curve, this is from 0 to about 10 or 12 megaparsecs or so, we're essentially entering the regime where the first term is perhaps subdominant over the second term. And then by going further out to even larger scales, as indicated by this pink line, we are essentially entering to the region where the density of within that radius is close to the mean. So by looking merely just at different scales, we are changing the balance between these two terms. And therefore, if you look at in this G factor versus omega m diagram, we see the contour not only shrink from looking at the inside to the outside, but also it rotates. So we're essentially, by looking at different scales, we're able to change the balance between essentially omega m versus other terms as illustrated here. And this is kind of nice in a way that it has the capability to self-constrain or break the parameter degeneracy, at least illustrated by this parameter space. So let me finish by putting a summary here. I hope I convince you that this exercise of combining lensing and redshift space distortion around spherical regions in principle allowed us to test the spherical dynamics in a cosmological dependent manner, and is in principle free from initial conditions. And also, in principle, there's no need for a bias model because we measure it from data directly. And also, by going into the full nonlinear dynamics, we enter the small scale regime, and perhaps this would allow us to gain more information. And let me just put my caveats here and stop. Thank you.
We have time for a few questions. Ben?
Hi. So have you looked at opening up the, so how did you sort these into distances? How did you stack the voids when you calculated the correlation function? Because I guess you had to assume a cosmological model. Or I mean, the next question being, can you open that up and then use this to do an AP test, which would combine this together?
Yeah, I quite agree. In principle, you have to exercise the AP test, essentially accounting for the distortions of voice due to the assumed wrong cosmology. So yeah, RSD and AP has to be analyzed simultaneously.
I was just saying it would be much more sensitive to the cosmological parameters that way because the AP test gives you a very strong constraint on that.
Yeah, possibly.
You showed the peculiar velocity prediction for the spherical collapse, right? How accurate are they compared to the simulations?
That's a good point. So we have an earlier paper also done by Vasily Demchenko, a student of mine, specifically testing these aspects. And it's not fully satisfying in the sense that we find that for underdense regions, for voids especially, only the relatively large voids would agree, like the prediction for large voids would agree with simulations, but relatively small ones, they are not. And there's various of reasons for that, including the tidal field, for example, and the individually voids, we know that they're far from spherical, and so all these corrections we're actually still looking at.
Okay, if there's no further questions, I suggest we thank all of the speakers again and then break for lunch. I think we're back at 2 o'clock.
There are some periods